I don't know if it works. Anybody want to check the stream? See if it works. Okay. It says check. Yo, what's up? It's like this and like that. Come on. No, I'm just kidding. Okay. All right. So here we go. Share the stream. There it is. Copy. All right. There we go. Go to our canvas. And we'll just check real quick. If you're just coming in, make sure you sign the roster so you get your extra credit. Grab some candy if you want. And we'll get started in just a minute. Okay, cool. Ooh, yeah. Want to be my friend. Okay. Announcement. Okay. Give me 30 more seconds and I'm done. Okay, just setting up. Okay, and the 935 class. All right. Somebody should do for extra credit, set this up for me ahead of time. I should have told somebody to do that. That would have been hot. I mean, awesome. And hot and wonderful. That's on the live stream, by the way. All right, okay. Everybody say hi. Hi. You guys are so enthusiastic. Okay, you have a test tomorrow. Okay. All right, I think it's ready to go. Okay, so actually, let me just check, right? So we can see that we can hear something. And so I'm going to pipeline, going to Canvas, going to announcements. And live stream right now. Okay, let's see. Click here to watch the live stream. Click here. Watch the live stream. Wow, that's right. Awesome. The sound quality is pretty good. Right. Awesome. The sound quality is pretty good. Don't you agree? Look, sounds much better. Okay. All right. Good. Great. Okay. So we've got the study guide, and then we also need preview. Okay. How many people want to start with the preview questions? Anybody? Everybody got to see them already, right? Okay. So we won't do that then. We don't need to do it. That was a joke. I'm going to do that first. Okay. You want to do that or no? Advanced questions. Okay. Download that. Download that. And then the study guide. Download that. Okay, it doesn't hurt, right? You could go over these questions again. Okay, quick review. These are questions that are going to be on the final exam. So should you know them? Absolutely, right? Question number 1. This is live streamed right now, so you can tell your friends, go onto the live stream. You can actually check it out. The lowest mass red dwarf. Okay, just to interject, because you're here to study, can I interject? What is the classification of a lowest mass red dwarf? What classification? That is an M-class star. If you forgot, maybe just make a note. I think you should know that. A red dwarf is an M-class star. The coolest stars. They have a mass. What's the smallest mass star that you can have that lights up that is a red dwarf? 0.08 solar masses. You're supposed to memorize that number. That's the smallest mass that will actually light up. The lowest mass red dwarf can theoretically live as long as, the right answer? 5.5 trillion years. Okay, 5.5 trillion years. Please engage students rather than just give them the answers. Oh, you're not supposed to see that. Okay, here we go. The figure below shows a binary star system. One of the stars has a larger mass than the other. Can you tell that from the picture? Do you understand it? So, and actually, how would you know that? What do you notice about the picture? How do you know that they don't have the same mass? Their orbits are different sizes. So which mass is bigger, star A or star B? Star B is a larger mass star, so it makes a smaller orbit. Does everybody remember that? It's closer to the center of mass, right? So now, what's going to happen? It says this is called a spectroscopic binary. It's one of the ways that we see that stars are made of two stars, not just one. You can't see the two stars, but you can see their spectra and the spectral absorption lines, actually. So when you have a star coming towards you, what happens to the frequency of that spectra? It gets shifted to a higher frequency, right? Raise it up. It's called the blue shift, right? Higher frequency blue shift. When the star is moving away from you, we see the same lines shifted to a lower frequency called a red shift. The faster the speed, the greater the shift. So in this question, which star will have a greater shift, star A or star B? Star A, because it's moving faster. It's moving on a bigger circle in the same amount of time as the other mass moves on a small circle. So what kind of a shift should star A be? A red shift. A bigger red shift or a smaller red shift? A bigger red shift because it's moving faster away from us. The star B moving towards us will be a blue shift, but it's a larger mass. It doesn't move as fast. So it'll be a smaller blue shift. Okay, look for it. Neither star shows Doppler effect. Wrong. Okay, star A's, I have to read these because I scrambled them, I think. Star A's spectral lines have a smaller red shift. No, larger red shift. Okay, star A's spectral lines have a larger red shift, while star B's spectral lines have a smaller blue shift. Everybody hear the answer? Okay, red shift, blue shift, stars coming towards you. It's a blue shift. Going away from you is a red shift. Which of the following can occur periodically? Oops, I think I changed the word, darn it. I didn't like the periodic thing. Okay, because sometimes people think it has to happen in the same amount of time, but what I really meant is more often than once. I think I changed the words. That's not fair. I have to change them back, don't I? Shoot, darn it. Okay, the way that I wanted to say it is which one can happen more than once for an individual star? Okay, does anybody know what the right answer is? A nova, right? What is a nova? You're supposed to remember what nova means. A small white dwarf is pulling matter from a neighboring red giant. And every time it does, it fuses that and you get a flash of light called a nova, okay? And it can happen more than once. Can it happen forever? If the mass of the white dwarf is small, yeah, it could pretty much happen, well, not forever, for a very long time, but or red supergiant, something like that. Yeah, white dwarf with something giant. Yeah, the giant means that the mass is going to be far away from the center. But the answer to your question, it's going to be a red giant, or it's probably going to be a red giant. Do you know why? Can anybody tell me why? If it was a red supergiant and it blew up, what kind of a supernova would it be? A type 2 supernova, which would probably blow away the other star if it's that small. So it's likely that it's two smaller mass stars that are orbiting each other. So the red giant is actually the most probable version, okay? Anyway, so nova happens more often, can happen many times. Type 1a supernova occurs when, I'm just reviewing with you so it doesn't hurt, right? What happens? Type 1a supernova. That white dwarf steals just a little too much mass and it goes over the limit. Who knows the limit? The Chandrasekhar limit. 1.4 solar masses. Okay, if you go and fact check me, you're going to find out it's not exactly 1.4. That's okay. Remember, this class is about. All right, type 2 supernova. What's that? Type 2 supernova. A massive star goes all the way. What do I mean by all the way? All the way to iron. Tries to fuse iron, and iron doesn't release energy, so the core collapses even faster, and you get a big explosion with the leftover material outside of the core. And we call that a type 2 supernova. What is the mass of a star which leads to a type 2 supernova? I just saw somebody mouth it, but give me the words out loud. How many solar masses do you need in order to go type 2 supernova all the way to iron? Because you're going to have enough mass to keep fusing heavier and heavier elements. It is 8 solar masses. All right, you knew that. Right. So 8 is kind of like the boundary. If you're under 8, you're not going to go supernova. Not at first. You might do a white dwarf. You might be a white dwarf that goes supernova, but you will not do a type 2 supernova. Greater than 8, all the way up, anything above that is going to be type 2 supernova. Formation of a neutron star is what happens after a type 2 supernova. Formation of a white dwarf is what happens after a red giant stage. And so the nova is the only one that can happen more than once, right? It's the only thing that can keep happening. As long as the white dwarf is stealing matter from the red giant, you can get a nova. Okay, number 4. Is everybody good? The answer was nova. Nova. They may be scrambled, the answers, right? But you know the right answer that you're supposed to give. Why does stellar fusion of massive stars end with an iron core? So we just mentioned that is, you've gone all the way. You've gone as far as you can go. Why does iron stop it? The fusion of iron does not release energy. It absorbs energy. So we need fusion to release energy to fight against gravity. So if you don't do that, then you're not going to be able to live anymore. You're going to die. So it's a fraction of a second after you start iron. And the iron doesn't fuse, not all of it, just a small little piece of it. And it's enough to destroy the star, okay? So you're left with a big iron core. When you get a chance, sign the roster, you get your extra credit, grab some candy if you want. Okay, so the answer is iron requires such a high temperature. Well, that's true, but that's not the reason, right? Iron cannot undergo fusion. Yes, it can, but it doesn't release energy. The core becomes so hot it expands, whatever, no. And the last one, iron does not release energy when it undergoes fusion. That's the key, right? It doesn't release energy. And therefore, you can't sustain a star anymore. Gravity's going to win. All right, here we go. Number 5, we saw a picture last week. That was pretty cool. The picture of a black hole. Can you see the black hole itself? No, the event horizon prevents light from escaping. But if material is falling into the black hole, for a little while, it will orbit in the area around it. We call that the accretion disk. And so as it does, this is called the accretion disk. It heats up dramatically, like 1,000,000 Kelvin or even hotter, right? And that's going to emit X-rays, okay? So we see X-rays. When we first started looking with X-ray cameras, we discovered there's black holes all over the place, much more than we realized. Questions? Okay, so you don't usually see the optical, you see the X-ray. Okay, here we go. This is a topic called general relativity, which says that as you go deeper into a gravitational field, a clock will tick slower. And I'm watching from far away, right? I'm not in the field itself. I'm watching a clock go deeper into a field. I'll see the clock tick slower and slower. The deeper it is, the stronger the gravitational field, or the greater the acceleration. They're equivalent. Remember, Einstein said there's no difference. So it could be just a rocket accelerating with a great acceleration. That kind of a clock would tick slower as well. Okay, so 2 very precise clocks. This is on your test. So just read the lot of words that there are. 2 very precise clocks are synchronized at sea level. Clock A is kept at sea level. And clock B is taken to the top of Mount Everest for a year. Mount Everest, you're supposed to know, is a mountain, which is further away from the center of the earth. Everybody get that, right? So is it higher or lower? Well, it's higher. So what happens to the strength of gravity as you move away from the center of the earth? It gets weaker, right? So if it gets a little bit weaker, what should happen to the clock? It should tick a little bit faster, not slower, because it's going away from the center of gravity, right? Okay, so clock B, well, all right, so there's so many words. Okay, then B comes back to sea level, and they're compared. Which of the following would be expected as a result of general relativity? It's called gravitational time dilation. Okay, clock B will be behind clock A because it has been running slower. No, it's actually running faster, right? It runs faster, higher in the in a smaller gravity that it experiences at the top of the mountain. So it won't be behind because it's slower. That's just, oh, wait. Clock B will be behind. No, if you run faster, you're ahead, right? Okay. Clock A will be slightly ahead. No, clock A will be behind. It's running slower. The two clocks will be synchronized? No, wrong. And D, clock A will be behind clock B because it has been running slower. Deeper in the gravitational field, clocks tick slower. That's the key idea, okay? I make it simple? I mean, you got the question already. You have nothing to worry about. You got the one question I probably asked. Maybe there's one other on general relativity, so don't panic about that. I know it's hard and confusing, but you don't have to worry about it. This chart is in your on your exam, and it's not just one question, right? It's a set of questions that goes with this table. So you want to understand, I've given you one question, but you might actually, if you're a good student, think about other questions I might ask you from the very same information, okay? And we've talked about it, but I'm just trying to say heads up, right? There's more information. We could talk about it in a second, what's important, right? So it says here, from the data given, which star in the table would appear the faintest in the night sky? Now, I didn't say from Earth, but you understand I meant from Earth, right? Everybody understand that? So which column are you looking at because of the question? You're looking at the first, the second, the third, the fourth, fifth. Which one? The first column, you're looking at the apparent magnitude because that's what apparent magnitude is, the brightness of a star as seen from Earth, right? What do we see from Earth? And how does the magnitude scale work? If a star is bright, what happens to its number? Low or high? It's going to be lower. The brighter it is, the lower the number will be. And if it's dimmer, the number goes higher. So you look at the chart, which one is dimmest? The biggest number or the smallest number? The biggest number, the highest number. And what's the highest number in my list? 4.2 is the biggest number that I see. Does everybody see it? So that would be the dimmest star. What's the brightest star? Suppose I ask you that question. This one is the brightest, right? So dimmest, 4.2, brightest, negative 1.5. Everybody good? So bright and dim works that way. So from the data given, the right answer would be HR 2491. Keep in mind, there are more questions on this. Anybody think of another kinds of question I might ask you about? Yeah. What was that?
Just for the faintest one, so would that
The number is 4.2 is the largest number.
you said D.
Oh, I'm sorry, messed up. 65 tau. Ooh, I don't know why I just read that. Sorry about that. Okay, it is, ooh, sorry, I just messed up. Hey, you guys at home, I just made a mistake. Thank you for catching that. It's 65 tau, the largest number, okay? The largest number, thank you. Thanks for catching that. Everybody heard that? So don't make, oops, wow, that's the exactly wrong one. Okay, what other kinds of questions could I ask? What happens when you compare absolute magnitude to apparent magnitude? What can you figure out? The distance, right? So you can figure out distance. If you have the apparent magnitude and the absolute magnitude, you can figure out the distance. So what happens when let's say you look at the two numbers, right? Let's say your apparent magnitude is a 5 and your absolute magnitude is a 1, right? What does it mean? What does it tell you about the distance? Is the star located closer or further than 10 parsecs? So the apparent magnitude was a 5. Is that what I said? Yeah, and then the absolute magnitude was a 1. The star is further than 10 parsecs. What is absolute magnitude? The apparent magnitude when you move the star to 10 parsecs, about 33 light years, 32.6 light years, right? So when I moved it to 10 light years, I got 10 parsecs, 33 light years. It got much closer. That's why it appears brighter. 1 is lower than 5, right? So it got much brighter. Things like that. I don't know. There's too many things. What's the other question I could ask? What about absolute magnitude? What do you think about when you see absolute magnitude? Why do we have different numbers there? Absolute magnitude. What is it connected to? There's a word I'm hoping you connect absolute magnitude to. You said, nah, it is connected to that, but that's not the word I'm looking for. Luminosity. Luminosity. So what if I ask the question, which is the most luminous star? Which star has the greatest luminosity? What does that mean, right? The star puts out more light per second than any of the other stars. What's the right answer for that? What's the greatest luminosity star? So you're going to look for the lowest number because absolute magnitude is only affected by luminosity. So the stars with the greatest luminosity have the lowest numbers. The stars with the smallest luminosity, they're not shooting out a lot of light, are going to have higher numbers. So the answer would have been 58 Ori. Okay? All right. Okay, really important questions. And I played with the words on this too. Oh well, I got to fix that. Okay, what force supports a neutron star with a mass between 1.4 and 3 solar masses against the force of gravity? What keeps gravity from collapsing it? The neutrons. Yeah, the neutron degeneracy pressure. If it says neutron star, you want to remember the neutrons are what's holding it up, keeping it from collapsing. But if you go above 3 solar masses, what force keeps gravity from collapsing it? If you go above 3 solar masses, what's the name of the force that stops gravity? There is no force that can stop gravity at that point. Nothing, right? You can't stop gravity. What do you form if you have more than 3 solar masses at the end of your life? A black hole, right? So there's nothing. Now, the other question I could have asked is, what about a white dwarf? What keeps a white dwarf from collapsing? You guys know the name? It's the electrons, right? What is it? The electron degeneracy pressure, and that answer is up there, but don't pick that for neutrons, right? That's for a white dwarf. All right, next question. As a graduate student, we just learned about her, Jocelyn Bell Burnell, and her advisor, Anthony Hewish, who ultimately received a Nobel Prize for his work in 1974, or for this work. Sorry, he didn't do the work. She did the work. He got the prize. That's cool. But she finally did get recognized, right? Not that long ago, a few years ago. Is credited with the discovery of the first rapidly rotating neutron star, which she detected with a radio telescope array. What did she call them? LGMs, little green men. Okay. The rapid rotation, together with the powerful magnetic field, produces twin beams of energy called jets, right? Which radiate, oh, I misspelled. Wow, cool, thanks. All right, which radiate away from the object. We call this a pulsar. Great. I think I'll fix the spelling. Sorry about that. That's funny. I really try to edit and I still miss stuff. How about that? Okay, number 10. If star A has an apparent magnitude of 8, while star B has an apparent magnitude of 13, then star A is brighter or dimmer? Much brighter, right? 8 is lower than 15 by how many? 13 by how many numbers? 5 numbers. And 5 numbers is one of the combinations you're supposed to remember. How much brighter is it? 100 times as bright. 100 times brighter. A is 100 times brighter because you dropped by 5 magnitude numbers, right? 13 down to 8 is 5 number drop, okay? So one drop, a drop of 1 number, how much brighter? 2.5 times brighter. A drop of 2 numbers, it's 2.5 times 2.5, not plus, right? 6.25 times as bright. And a drop of 5 numbers is 100 times as bright. Okay, those are the 10 questions that will be on the exam. Okay, if you just came in and you missed them, we can do them again at the end, all right? Or look at the live stream, and it's recorded now, or it will be. That's cool. Man, it makes me look good, right? Oh, now I got good sound. Check it out, check it out, check it out. All right, let's talk about that study guide. Let's talk about the study guide. All right, here we go. So don't forget, I did actually talk a little bit about a mission at the end, which is still in our solar system. Don't forget, there may be a question. Hint, hint, definitely. It's on the study guide, fair game, okay? All right, anyways, so it's supposed to know a little bit about Pluto. What do you know about Pluto? Pluto is actually called a what kind of planet? A dwarf planet. That's not up there, but anyways, okay. So what's the name of the mission that flew past Pluto? It flew past it, called New Horizons. Okay, you're supposed to know the name. New Horizons flew past Pluto. And as it did, it took lots of pictures and beautiful imagery and spectroscopic data. It scanned the surfaces and analyzed what the atmosphere was made of. It was really cool, amazing. It took a year and a half to get all the data back. And supposed to know that Pluto is technically a Kuiper Belt object, right? It's an object in the Kuiper Belt. Kuiper Belt is outside of the orbit of Neptune, just past Neptune. Trans-Neptunian objects, another name for it. So Pluto, its major moon is called Charon or Chiron. And what's Ultima Thule? What the heck is that? Okay, New Horizons. Did it orbit Pluto? Did it stop in orbit? No, it just shot past at high velocity, and it wasn't finished. It still had fuel. It still had batteries. It's got power. And so it went on to the next mission. And the next mission was a little tiny body, which we really haven't heard very much about. I'm kind of disappointed about that because I thought we were going to get all this great information, but it's really slim right now. I'm not sure why. They maybe didn't find out that much. I don't know. Anyways, they found out this is the first time we've ever seen a Kuiper belt object up close. Okay, so that's all it is. Just supposed to know that. All right. To describe some of the major discoveries made by New Horizons, how has this changed our understanding of the Pluto-Charon system and KBOs in general? So what do you remember? Was Pluto kind of boring, or was it full of features? Full of features, all kinds of things, mountain ranges and plains and interesting structure that we never anticipated, right? Including the largest glacier in the solar system, right? Pluto has the largest, it's the big heart on Pluto. It's the largest glacier in the solar system. What is it made of? Nitrogen ice, not water ice, okay? In fact, do you find any water ice on Pluto? Okay, that was a trick question. The answer is absolutely yes. What's made of water ice? The mountains, right? Just like on Titan, the mountains on Pluto are made of water ice. So water is acting like rock, right? The rock on Earth is now water ice on Pluto. It's always so cold, it acts like that. Okay, what's special about, okay, anything else that's cool? Nitrogen, atmosphere, some organic compounds. There's not a lot of stuff, okay, but a few things. What else? What else is important? Anybody? Can't think of anything special. Oh, how many moons does it have? 5 moons, 5 moons. Do you remember the problem? Did we get a lot of great pictures of all the other moons? No, because the orbits are kind of chaotic. Except for Charon, the other moons have chaotic orbits. They're not easily predictable. In fact, they're not predictable. So that's a problem. Okay, what is tidal locking? What does that mean? A moon is tidally locked. It means one face is always facing the planet. But what's special about Pluto and its moon, Charon? They're tidally locked to each other. So that's the first time we've seen that with a planet, right? So the first planet we've ever seen. But we know that it's going to happen eventually to most bodies, okay? And I think I've covered it, okay? That's all the stuff from before. Moving right along, chapter 10, okay? I'm assuming we should go in order, right? You guys want to go in order? Okay, we're going in order. Okay, so the first thing was the sun. All the stuff about the sun, okay? The sun, first of all, is it a ball of gas? No, right? We heard the song by They Might Be Giants. The sun is a miasma of incandescent plasma. That's the word, plasma. What is plasma? Plasma is charged matter, right? You had, actually the line that I really love is electrons are free, right? The electrons are pulled away from the atom to make it a charged atom. So you got electrons, you got these ions. It's all this big mess of electrically charged stuff. And actually, immediately, as soon as I hear the word electric, does everybody remember that the sun is rotating? Right? Rotating body with electrically charged stuff. What do you think about? Do you think about no? I really hope. The dynamo effect. Yeah, how many people think of the dynamo effect? That's what I want you to, okay, that's it. That's like the key cool thing, right? Charged matter circulating creates magnetic field. The sun has a profoundly powerful magnetic field, okay? So anyways, that's the first thing I think about. Thermonuclear fusion, what does that mean? Thermo, heat, nuclear, nuclei, right? The joining together fusion under the presence of a lot of heat energy, right? So why do you need a lot of heat energy to make nuclear fusion occur? So these are ideas, right? What kind of fusion happens with all stars in the beginning? What kind of fusion? The fusion of hydrogen into helium, right? Every star begins in the core fusing hydrogen into helium. But hydrogen is positive, negative, neutral. Which one? It's just the protons. It's just the positive core. And so do the positive cores want to get together? They repel each other. So how do you get them to get close enough together to join? You have to smash them together with a high velocity. And that comes from a high temperature, right? Or high density. Okay, hydrostatic equilibrium, what does it mean? Did we answer the question? You guys good? Thermonuclear means the fusion that takes place under high temperature. And it's the joining together of nuclei to form larger nuclei, fusion. Okay, hydrostatic equilibrium. What two forces are involved when we talk about hydrostatic equilibrium? Gravity's pulling in. What force is balancing gravity? Radiation pressure. As long as the star is alive, radiation pressure is pushing out stronger, weaker, or the same strength as the force of gravity. The same strength. It balances, right? It's called hydrostatic equilibrium. So it's exactly balancing. Okay, so radiation pressure is the idea that, well, it's a force which balances gravity, number one. But number two, how do you generate radiation pressure? How do you make it? Where is it made? In a main sequence star, where do you make the radiation pressure? In the core, where the energy is being released by the nuclear fusion process. So the heat energy pushes, well, you create light and heat, and it's going to be able to push out against the force of gravity. We don't actually worry too much about it, but I think you've learned something important. If you make a photon inside of the core and you try to get it out, does it get away very easily? It doesn't get away. It takes 100,000 years for the energy that was that photon to eventually escape. So it doesn't, I think I forgot a word. I did forget a word. Oh no, there it is, neutrino. Who knows what a neutrino is? What's a neutrino? Tiny little particle, right? Tiny little particle, we did talk about it. It's a tiny little particle, and they're produced in nuclear fusion as well. What happens to them when they try to escape? They have no problem whatsoever. They go right out of the star. And we are being showered with them all the time, right? The neutrinos are coming from the sun. Day and night, we get about the same amount because they go all the way through the Earth without stopping. The neutrinos. Anyways, okay. Differential rotation. What are we talking about? Differential rotation. The sun rotates at different rates. Okay, so it rotates faster where? Equator or pole? Equator. Fastest at the equator, 25 days to make one rotation. And the pole is a little nebulous, 34, 35 days, something like, I don't even know, something like that. I don't care if you know exactly what, no, I don't know what it is either. But it's much slower at the pole, 34, 35 days, okay? Whoa, okay, now we're jumping down to the pieces of the sun, right? So what's the core? The core of the sun? This middle part of a star, right? The core of a star, the core of the sun, where nuclear fusion is taking place, right? It's the hottest, highest density place in the star. About how hot is the core of the sun? What's an approximate temperature? Approximate. Hydrogen fusion needs this temperature to work. 10 million. No, you're talking about the surface. Yeah, that's the surface. That's okay. Try to keep it straight. The core is about 10 million Kelvin. That's what you need to fuse hydrogen. I'm just giving you a rough number, okay? It's a little hotter than that, don't worry, okay? But anyways, 10 million Kelvin is enough to fuse the hydrogen in the core. Do you remember what happens when you get rid of, when you finish up the hydrogen? What will you have a lot of in the core? You'll have helium ash. Remember the word helium ash, right? So the helium that forms is called ash at first. Is that a fuel? Not at first, right? Because helium has a charge of +2, and so it's harder to make them combine, right? +2 doesn't want to get together with another +2. It's 4 times as powerful a repulsive force. So you need a much higher temperature. Okay, so again, you don't have to know these numbers necessarily, but you know that it's more than 10 million. Does anybody remember the temperature needed for helium fusion? 100 million, right? That's a pretty big jump. So the bigger the nuclei, the harder it is to make them fuse. You need 100 million Kelvin to fuse helium. And if you wanted to go to the next level, fuse helium into carbon, what would the temperature be? Again, you don't need this, but it'll help you to see like how big a jump it is. Anybody remember? 500 million Kelvin, right? It's like a really big jump every time. It just gets bigger and bigger because of the difficulty to join together bigger and bigger charges. Okay, core, we got that? It's the middle part of the star. Just outside the core, this is where you're making your energy and the radiation pressure. So when you try to get away, those light particles and the energy tries to get away, it's trapped in this area called the radiative zone. How does it work? Well, the radiation is trying to escape, but it doesn't get out very easily because it's very dense. And so in this mechanism, we're actually generating the pressure as the light is trying to escape. That's generating the pressure. So the radiative zone is what process is primarily taking energy from the middle and moving it out? What mechanism? You got conduction, convection, or radiation? Okay, I hope you say radiation for the radiated zone, right? Doesn't that make sense? It's radiation. Okay. Right above the radiative zone, it turns out it's more efficient for the star to move matter and carry the energy in a fluid called the convective fluid. And so it's called the convective zone. How does energy move in the convective zone? Through convection. Okay, it's pretty obvious, right? So how far does the convective zone? Does it make it all the way to the surface or no? Yes, it makes it all the way to the surface, and we can see the tops of the convective zone. Each cell of convection is called, got a name, called a granule or granulation. Granulation, right? That's a single convective cell that we see at the surface of the sun. Okay, so I'm kind of mixing things up. Sorry about that. But anyway, what's this photosphere? What's that? Photosphere. Photo means light. Sphere. It's the surface of the sun that we see that's emitting light. It's the sphere of light that we see from the sun. That's really the surface of the sun. Okay. Just outside this photosphere, we have the chromosphere. What is this? This is a little bit of the atmosphere of the sun, and it is glowing. What color is it? Who knows what color it is? Yeah. Green? No, not green. That's you're thinking of the central peak. That's the central peak. But the chromosphere, which is just outside the photosphere. By the way, the photosphere is white, right? The light that we get from the sun is white. It's a mixture of all the colors of the rainbow. But what's the color of the photosphere? Pink, right? Pink. And what it is red on top of all of that white coming from the sun. So it looks pink. What is the red coming from? Help me out. Red, you're supposed to know this. Hydrogen alpha. Hydrogen alpha. Excited hydrogen gases glow red. Are they ionized or neutral? They're ionized. They're hot. Ionized hydrogen gases, kind of like one of the interstellar mediums we'll talk about in a few minutes, right? Does anybody remember the name of the interstellar medium, which is made of hot, ionized hydrogen gas? The photosphere is white in color. Yeah, if you could analyze that, right? It's all the colors of the rainbow mixed in, right? So anybody remember the name H2 regions, right? H2 region is a hot ionized hydrogen that's glowing pink, pink and red, okay? All right, chromosphere, corona. What's the corona? Corona, right? The outermost layer, very low density layer. You can't even see it most of the time, but it's very low density, very high temperature. Anybody remember the temperature? Because we keep getting the same word corona, it would be nice if you remembered roughly the temperature. It's about 1,000,000 Kelvin, 1,000,000 Kelvin. So coronal gases, whether they're around a star or near a galaxy, we're talking about really high temperatures. Near a black hole, right? That can be about that. Okay, so what is the strong nuclear force? Actually, I feel like maybe I should take just a second to remind you about the forces you're supposed to know. But you want to do that or no? Anybody? Okay, so let's take a second here. Let's move this over here. Look on the board so we can show our audience at home. Hey, audience at home, how you doing? Live control. Oh, there we go. Look at that. Look at that board. It's blank. There's nothing there, but you can hear me perfectly now, right? This is awesome. Okay, I'm glad they can hear me. Okay, what are the forces? There's 4 forces. Number 1, the one that organizes the universe is called gravity, okay? The longest range force, but also one of the weakest forces. Long range, but weak. Long range, but weak. Okay, what's stronger than gravity? And it's actually enough to hold atoms together, right? Positive attracts negative. That's the name of the force we're talking about. The electromagnetic force. Electromagnetic force. The electromagnetic force. Okay, so it's pretty strong, but it doesn't go very far. It doesn't reach very far. It's kind of a short range. Short range. So you don't usually feel an electric force when you're a little distance from something because most of the matter that we deal with is neutral. So you just don't get that, right? All right, now we're going to get to really short range, really extremely short range. So number one, the strong nuclear force. What does it do? What is the job of the strong nuclear force? To hold the nucleus together, right? It holds the nucleus together. So even though the protons want to fly apart, there's a force that's stronger than that. But it has a really short range, right? Extremely short range. It only as far as a nucleus. So it's a really powerful force, but very, very short range. And the last one is called the weak nuclear force. Okay, and what is the weak nuclear force associated with? Actually, I think it would be good to associate it with neutrons and something I told you about. If you remember, if you take a neutron and you take it away from an atom, is it going to stay like that? Do you guys remember this? It's incredibly unstable. 10 minutes is the lifetime, right? 10 minutes is the half-life. What happens to a neutron? It decays into a proton plus an electron. So that's what happens, right? So what does the weak nuclear force do? It's somehow holding together quarks to form larger particles, right? It's related to that. So the weak nuclear force holds protons and neutrons together. All right. So that gives us a little bit of a framework, right? So which force is responsible for making hydrogen fuse into helium? Which force is actually the one doing that? Anybody? That would be the strong nuclear force, okay? The strong nuclear force. So when you get the nuclei close enough together, they would repel each other, but if you get them close enough together, the strong nuclear force is more powerful and joins them together. Okay. Proton, proton. Proton, proton, and then right after it, CNO. What are those? Yeah.
I was wondering if you could give an example of where you find the electromagnetic force.
The force that attracts electrons to protons or to the nuclei is the electromagnetic force. So it holds an atom together, or chemical bonds, right? Chemical bonds between atoms is an electromagnetic force.
The difference between that and a strong nuclear force is that the strong nuclear force only holds
inside of a single nucleus, yeah. Yeah, so not between atoms, right? So electromagnetic force would be between atoms, like that. Okay, so what's proton, proton, PP, and CNO? What are those? Two names for nuclear fusion of hydrogen into helium, right? It's two ways that stars, which kind of stars are fusing hydrogen into helium in the core? That's another name for a main sequence star, right? Remember main sequence, fusing hydrogen in the core to create helium. And so there's two ways. Are they different in the amount of hydrogen that they use or the amount of helium that comes out? They're not. They're exactly the same. How many hydrogens go in? 4 go in and 1 helium comes out. But they're different, right? So which one is the dominant process in a star like our sun? In our sun, which is a smaller mass, less than 1.4 solar masses. But I won't make it so close. It won't even be close to the boundary if I ask you this question. What's the right answer? PP, right? PP is for small stars. Larger stars use CNO. And there's a word that we use in CNO. Do you remember the word? It accelerates the process. It's called a catalytic process. So what it means is it can speed up the chemical reaction. You get a faster rate of fusion. Okay, CNO is a faster rate of fusion. So larger mass stars can use CNO and produce more energy in their core, which means a larger mass star is what happens as a result of the greater energy. They end up being hotter, right? They're hotter stars. So hotter stars use the CNO. Cooler stars will tend to, I mean, they both use both, by the way. Every star uses both. But in our sun, for example, 90% of the energy is from PP and 10% is from CNO. But if you take a very large mass star, it might be flipped. It would be the other way around, or maybe even more. Okay, what's antimatter? Is it real? Antimatter, you're supposed to know this. Is it real or not? It's absolutely real, right? Every particle of matter has another particle called its antiparticle pair, right? Or a partner, whatever name. There's another particle that's the antiparticle of that. So if you look right here, I have the name positron. And a positron is a positively charged particle. It is the antimatter particle of what? The electron, right? A positron is the antimatter version of an electron. It's not an electron, it's an antimatter particle. So what is the symbol that we use for a positron? Anybody remember? Yeah, E plus, right? And the symbol for an electron? E minus. And I find this to be really exciting, so you have to know this, right? If you take an E positive positron and you say, hey, let's make friends with an electron, E negative, what happens? You get a beautiful explosion, right? They annihilate one another. They're gone. Only thing left is the energy. So what is the mass of a positron? Is it the same or different from the mass of an electron? Same mass, different charge, and it's an antiparticle. When this one finds this one, annihilation. I'm going to spell the word. ANNIHILATION. And it's actually just pure energy. It could be photons, it could be other particles, but anyways, some kind of energy. Okay? So positron meets an electron, you get annihilation. If an antiproton meets a proton, you get annihilation. If antihydrogen meets hydrogen, you get annihilation, right? What happens if a positron, which is an anti-electron, meets a proton? Nothing at all. It doesn't annihilate anybody except for its antiparticle version, okay? So that's not going to do anything. Okay, solar granulation, we mentioned that a little bit ago. What's granulation? When you look at a picture of granulation, I feel like we could just look at a picture. Let's look at a picture. Granulation. I should probably just show pictures. Why not? Google will show me everything. Oh, that's not right. Oh, that's wrong. Oi, that's ugly. Solar. Oh, beautiful. Oh, gosh, look at mesmerizing time lapse. Oh, that's awesome. Okay, there's a video showing granulation occur. It looks like boiling stuff, right? And so you can see that the granulations are the little patches, and the part that's in the middle is bright. What does it tell you? It's bright. It's hotter, and it's dark around the edge. Why does that? It's cooler. The matter is rising in the middle and falling on the outer edge. That's the way it's working, okay? You can see that. So when we see light or dark, we know that that's a difference in temperature, right? And that will segue into, ooh, that's cool. That's not, I should not do that. Okay, back to my work. Did you find something cool? Okay, so granulation, Maunder minimum. Okay, Maunder minimum, anybody? Maunder minimum? Sunspot activity, that's what we're talking about. Sunspot activity. So sunspot activity occurs in a regular way. Sunspot activity, who knows the length of time it takes for a cycle? 11 years, okay? Let's show some pictures here. Sunspot activity, okay. Sunspot activity, okay. That's pretty good. Oh, there we go. There's the picture, right? And what's Maunder minimum mean? There was a period of time when there were no sunspots. People looked for them, but they couldn't see them. There were no sunspots, okay? Why? The sun was especially quiet. Could it happen again? Yes. Will it happen again? We don't know. But it may happen again. It hasn't happened in a while. And so what happens is we get cycles of high activity and low activity, and the peaks are about 11 years apart, and the valleys are about 11 years apart, right? So it's 11 years for a cycle. So the solar sunspot cycle is 11 years. 11-year solar cycle. Sunspot, what is a sunspot? A cool area of the sun, right? It has a name for the innermost part. What's the innermost part? The umbra. Very good, the umbra, sunspot. Sunspot, let's take a look at a picture. Oh, those are beautiful. Oh, look at that. That's exactly what I want to tell you. The innermost part is dark. The darkest part is called an umbra. Why is it dark? It's cooler, right? And outside that, we have the penumbra. And then outside that, we have the sun, right? Why is it cooler? Who remembers the reason? And you should know the reason, right? It's like a little bubble, like a balloon. And if it's not growing or shrinking, then what can you say about the pressure inside the balloon and outside the balloon? If it's not shrinking or growing, the pressures are balanced. But it wasn't there when you started, right? It was really small. And then it grew, the sunspot grew. What made the sunspot grow? And the answer is extra pressure from magnetic field, okay? So the magnetic field popped out of the sun and made a little extra pressure, and that made the bubble grow. And as it grew, what happened to the temperature of the spot area? Because it's expanding, it cooled off a little bit. So the sunspot's a little bit cooler, but it has a little less pressure, thermal pressure, plus the magnetic pressure balances the inward thermal pressure from outside the spot, okay? All right, so everybody good? You got that sunspot thing? All right, kind of. All right. Okay, sunspot. Prominence. What's a prominence? I think I just show you a picture. I'll show you a picture. Why not? Prominence. Anybody remember? Prominence. Ooh, beautiful prominence. Look at that prominence. If you see a picture on the test, it might be hard to see. But if I show you a picture like that, what do you see? A big loop that goes from one side to the other. That's an example of a prominence. What is the material following? The magnetic field lines that are popping out of the sun. So there's a sunspot here, and there's a sunspot here at the ends of the prominence. Does everybody remember that the polarity of sunspots is either north or south? They're magnetic. And in fact, sunspots always come in pairs. So one of them is a north and one of them is a south. That's always true. Okay, that's a prominence. And then if you have the magnetic field twist on itself and separate from the sun, it seems to be escaping from the sun. What do you call it? It's not a prominence anymore. It's called a flare. A solar flare is a picture like, I guess that's pretty good. That's pretty good, right? Kind of like that. So the magnetic field is not coming down and arcing, it's kind of branched out away from the sun. So you see the energy escaping. In fact, what happened is the magnetic field pinched on itself and separated from the sun and is actually contained within the ionic material, the plasma that's moving away from the sun. So a flare carries energy and particles away from the sun. Now, what's a really enormous explosion that happens on the sun that you should watch out for? Anybody remember? CMEs, right? Coronal mass ejection. A solar CME. These things are magnificent, right? They're as big as the sun. They're huge, right? Look at the difference. It's not a little tiny thing. It's enormous. It's the size of the sun. Coronal mass ejection. These are the ones that are dangerous for life, right? When they flare really, really strongly for anything. Okay. Coronal mass ejection, flare, solar max. What's solar max? When you have a maximum of sunspot activity, okay? What happens at solar max? Does anybody remember? The sun changes its magnetic polarity at solar max. And then it spends the next 11 years with that polarity. And after that 11 years, it reaches the next solar max, it flips again. And so what about the magnetic cycle of the sun? How long does that take? It takes 22 years, right? So it'll be 11 years with north on the top and south on the bottom, and then another 11 years with south on the top and north on the bottom, and then it'll flip back again. It'll take 22 years to go through a complete cycle. So it's 2 solar maximums. Coronal hole is an area where we see coronal mass ejections often occur. Heliosphere, the magnetic bubble around the sun. Heliopause, the area just outside the bubble. Okay, so those are the terms. Okay, let's see if we can do some of this. I think we've talked about some of this, but let's just go through it. You guys, can you stop me if you need more detail? Do you need more detail? Heliosphere, the magnetic region around the sun. So it's like a bubble of magnetic field around the sun. The heliopause is the region just outside of that. So the magnetic field has finished, but we actually see some interesting stuff happen, right? Sure. Coronal hole is an area of the corona that appears to be dark, and it seems to be where the coronal mass ejections will come from. So it's almost like a prediction of where a coronal mass ejection is going to occur. So that's actually what we're looking for. We're hoping that one day we can predict them. We know exactly when they're going to happen. Okay, describe each layer of the sun and how heat energy is transported in that layer. Okay, so remember there's 3 mechanisms: conduction, convection, and radiation. Which one does not happen in the sun? Conduction. Why not? Because you need solid stuff. There's no solid stuff in the sun. So there's no conduction taking place. But you've got all this heat being generated in the core. How does it get away at first from the core? Through radiation in the radiative zone. At the top of the radiative zone, it's more efficient for the sun to mix. And so the larger the star is, the smaller this mixing region will be. The smaller the star is, the larger the mixing region will be. So, I mean, this is an advanced kind of idea, but if you have a red dwarf, one of the reasons it lasts so long is the entire body is convective. Okay, again, if that helps you understand why they last so long, that's a cool thing. But anyways, whatever. Above the radiative zone, you have a region where you're mixing the gas, the plasmas, and you're carrying energy from the top of the radiative zone to the photosphere, the edge of the sun. And that's through convection, called the convective zone. Okay, differentiate PP and CNO, and we did that already, right? So CNO, what does it stand for? Carbon, nitrogen, oxygen. They are generated as part of the cycle. Did they get used in the cycle? No, it's catalytic, right? It just helps the process along. But during the process of finally separating a helium, we go through those 3 elements along the way. Then we go back to being carbon again, right? So it kind of doesn't get used up. Explain why elements below iron release energy by nuclear fusion and higher elements release energy by nuclear fission. Okay, so do you remember what the most efficient element is? You're supposed to know. Iron 56. Yeah, with element number 26, but iron 56. This is the most efficient element. So everybody's trying to become more efficient. If you're trying to become more efficient and you're a little tiny atom like hydrogen, how do you get to be more like iron? Well, you join together with other atoms to become a bigger nuclei, right? So smaller atoms want to fuse, and when they do, they become more efficient, release energy. But if you're a big atom, the way you get to be more like a little atom like iron is by breaking apart. And the name for that is fission, right? So uranium is an example. In our Earth, uranium fission inside of the Earth is releasing energy that keeps the Earth warm, right? It's an important mechanism. Okay, but the idea is iron is somehow the peak of the efficiency of elements. Okay, explain how at each stage of its life a star establishes hydrostatic equilibrium. Okay, so what do you think? What does this mean exactly? At each stage. So if you're not in equilibrium, what's going to happen? If you're not in equilibrium, what will happen? You will change, right? If you're not in equilibrium, you will change, right? So in the very beginning, when the star is forming, is it in equilibrium? No, what's it doing? It's collapsing. And the gases are collapsing, and what happens to them as they collapse? They get hotter, right? Eventually, the protostar gets hot enough to slow down the collapse, and it stops collapsing so fast, right? It's still not a star, but it really has stopped its collapse for a little while. But anyways, as long as you don't have equilibrium, you're going to change. When you get past the main sequence of our sun, what's it going to be called? What kind of star will our sun become after its main sequence life? A red giant, right? Now, in a red giant, what do you remember? It's big, right? It's big and it's red. So big means what? A giant. It grew. And red means what? It's cooler than it is right now. And so why did that happen? Well, because we'll talk about it in a little bit, but what happens during that red giant phase is it's producing more energy than it did originally not in the core, but just outside the core in a shell, hydrogen shell burning. And so there's more radiation pressure than there is gravitational force. It's not equilibrium. And so it expands to find a new equilibrium position. So if the forces don't balance, what will happen? The star will shrink or grow, right? So whichever force is bigger is going to tell you what's going to happen. If gravity is bigger, what happens? You shrink. If radiation pressure is bigger, what happens? You grow, right? That's it. So they're always in balance, except when they're not. And if they're not, then the star will change size. Okay, what happens when matter meets its antimatter particle? What happens? Annihilation. Okay, describe convective flow. We did that as well. You see bright and you see dark. What does it mean? The bright means a little bit hotter in the middle, and the dark means cooler on the edge. So that's the way it flows, up in the middle and down around the edge of the granule. Explain how a sunspot forms and disappears. I kind of did that, right? What makes it form? The magnetic field popping out of the sun. Now, why does that happen in the first place? Why do we think that the sun's magnetic field pops out of the sun? Because it's getting tangled up, right? And it's getting tangled because the sun is not rotating at a single rate. So we think it's because of the idea called differential rotation, right? It's kind of tangling up the magnetic field. All right, so sunspots form, and when they form, there's a bubble around them, and then when the magnetic field goes away, they shrink back down and they're gone, okay? Describe how the solar magnetic field and the pole reversal is related to sunspot activity. At the solar max, the maximum number of sunspots, what happens? Poles reverse. All right, everybody good? And so you got to wait for the next one. Pole reverses again, right? And so on. So blah, blah, blah. Okay, 11 years between pole reversals, 11 years between sunspot activity. How many years for a solar magnetic cycle? 22 years, right? The sunspot cycle? 11 years, okay. Stages of a sun's life. Protostar, does that take a long time or not so long? Relatively speaking. Long or not? Not so long, maybe million years, right? Kind of like that. Actually, I don't know the exact. I think it's like million years. Main sequence, long or short? The longest stage or no? No. 10 billion years is pretty good, but it's not the longest stage. Red giant, long or short? Like 1 billion years, pretty long, but not the longest stage. White dwarf, for the rest of its life, which one is the longest stage for a sun-sized star? The white dwarf stage. Does everybody get that? The white dwarf, if you call it a stage of life, it's not really alive, it's dead. But anyways, of these stages, the white dwarf is the one that it spends the most time in, right? It'll be a white dwarf for a long time, for billions and billions and billions of years. Okay. The period of sun rotation, the length of time a photons takes to escape from the radiative zone, about 100,000 years. Okay? So hopefully memorize that. Oh, sunspot cycle. Oh, solar magnetic cycle. Okay, we did all this stuff. Good? All right, chapter 11. Talking about stars. Chapter 11. So the magnitude scale, pretty important. There's two kinds of magnitudes. One of them is called the apparent magnitude, and the other is called the absolute magnitude. The scale is still used exactly the same way. The way it works is larger numbers means what? Means dimmer star. Lower number means brighter star. Okay? And on the apparent magnitude scale, we talked a little bit about, what kind of numbers would be reasonable. You don't really need that, because I'll give you the numbers. But the only thing that you need to know for sure, can you see all the stars in the sky? Obviously not, right? There's a lot of stars out there. So we know that there's a limit to how dim a star is that we can see with our eye. Without any help, what is the magnitude limit for our visual perception? A 6. We say about a 6, right? Magnitude, apparent magnitude 6 is the limit of a human eye. You can't see a 7 or 8, 9, anything higher, right? But a 6 you should be able to see on a clear, dark night, right? If you're near light pollution, you cannot. In New York City, I can't even see more than a 3, right? It's just not going to work. The city's too bright. All right, Santa Barbara, pretty good. All right, absolute magnitude is the apparent magnitude at a distance of 10 parsecs. So that's a little bit different. And I should mention something, right? The apparent magnitude has 2 factors built into it. In the brightness of a star, we have the luminosity and the distance are both inside of that. So if you think about what makes a star bright, remember that there's more than one right answer. The right answer is, what makes a star bright? Really luminous or really close, right? Either one of those would work, right? If it's really close or really luminous, you could see it as a bright star. Okay, so, but absolute magnitude is different. Because you always put the star at 10 parsecs, what is the reason you have a high or low absolute magnitude? It's only one reason, your luminosity, right? So the stars that are high luminosity will be lower numbers, right? Because their magnitude scale works that way. And numbers that are higher will be stars with a lower luminosity, right? They don't have as much luminosity. Okay, what is a Cepheid variable? That doesn't say Cepheid variable, but that's what it is, right? What's a Cepheid variable? Henrietta Swan-Leavitt, right? She said that if you look at the stars, I messed this up the other day, but anyway, if you look at the stars that are variable stars, they change brightness. They get brighter and dimmer and brighter and dimmer. They have a period that they go through, a cycle to get brighter and dimmer. And so if you look at the period, it turns out the period is related to the luminosity. So what is the relationship? You don't have to know any numbers, but you need to understand the essence of the relationship. So here we go. Cepheid, I know I'm going to find it right here. Luminosity. I'm going to look for a picture, and I'm going to find it right there. Perfect. Okay, we don't need to go crazy. How crazy do you want to go? I like that one. That's pretty good. That's good. Okay, that's the idea. So the longer the period, the greater the luminosity of a star will be. If the period is short for a Cepheid variable, then it's not as luminous, right? That's all you need to know. This is a very qualitative idea. But the cool thing is, if you see a star that has this variable nature, by measuring the period, actually, this is the part you need to know. By measuring the period of a Cepheid variable, what will you know? You'll know its luminosity. And then if you know the luminosity, what do you know? The absolute magnitude. So why do we care? If you know the absolute magnitude, what do? You compare it to the apparent magnitude, and you can measure the distance. It's called the standard candle method, right? If we know the absolute magnitude, you compare it to the apparent magnitude, and you can calculate the distance. It's the best thing that we've ever done in science, right? Oh, I mean, in astronomy. Maybe not science. Okay. All right. Amazing. And now we have gravitational waves that work differently. Okay. Spectral classification. Oh, right. I got to get all this. Sorry, I messed up. Binary stars. There's 3 ways that we see binary stars. What's a binary star? A pair of stars that are orbiting each other. Okay. They may have the same mass or different mass. Doesn't matter. But they orbit a common center of mass, right? There are 3 techniques that we use to find them. One is called a visual binary, and I put down there some, but it's really small, right? In order to see a visual binary, you have to watch it for a long time and see them orbiting each other. It's hard. It takes a long time to do. The most common is this thing called spectroscopic binary, but this one is getting better too. So this one may end up overtaking it. I don't know. But right now, spectroscopic binaries is the best technique. And in that one, we see stars orbiting each other by their spectra. And this is one of the questions I gave you that's on the exams. So you want to get that idea. One of the stars will be moving towards us, And so what will happen to the spectral lines? They will be shifted to higher frequency, called a blue shift. And one of the stars at the same time will be moving away from us, and that will be called a red shift. So by looking at the red shift, blue shift, we can figure out what the masses of the individual stars are relative to each other. Okay, and the last one is called an eclipsing binary. And I just mentioned that. It is kind of cool, and it may become more important, eclipsing binaries. It's pretty neat. It's very much like when you detect an exoplanet. It's the same technique. Eclipsing binary. Oh, there's perfect. Great. Okay, so that's a little tiny picture. I get a bigger one. And I get a bigger one. That's the perfect picture, though. Oh, there's a good one. That's pretty good, I guess. That's a little bit better, huh? Oh, I shouldn't have done that. Sorry. Okay. Okay, so here's the picture. There's a big dip and there's a little dip, right? And the dip occurs because, why is there a dip? So the light curve is the total amount of light coming from the pair of stars together, right? What happens when there's a dip? There's less light. Why is there less light? One of the stars is behind the other one, okay? But you notice that the dips are not the same depth, right? Which one's deeper? When the hot star goes behind the cooler star, or when the cool star goes behind the hot star? Which one has a deeper dip? When I know it's confusing. There's a lot of words I just used very quickly. So the hot star puts out more light per square meter than the cool star. So if you block a hot star, then you will find out you're losing more light. Blocking a cooler star, you don't lose as much light. And so you can look at this picture and you can say, who got blocked? The hot star or the cool star? Hot star got blocked. And here, cool star got blocked. And here, hot star got blocked again. Okay? So then you look up and you see what's going on, and you can see that the small star is behind the big star here. But in this case, the small star is in front of the big star. Which one is the hot star? The small star is hot. The big star is cool. Okay? And actually, it gives me a big, it looks a lot like what? Anybody think of a combination that we've talked about before? White dwarf, red giant, maybe, right? White dwarf, red giant. Okay? That's an example of what you might see with a white dwarf, red giant pair. Okay? All righty. Proper motion. What's proper motion? Okay, that was a little tricky. And by the way, we don't measure it very often. It's very difficult to do. What's proper motion? When the star is moving in what direction? Towards us, away from us, or in a perpendicular direction? Yeah, that's what it means. It's not towards us. It's not away from us. It's to the side. And so how do you measure proper velocity? By watching it over time. You take a picture and 10 years later, you take another picture. 10 years later, that kind of thing. Maybe 5 years, but usually 10, maybe even 20 years later. It takes a long time. And then you see that little blip move, right? And you know, hey, that thing has got proper motion, proper velocity. Radial velocity, on the other hand, is much easier because what does radial velocity mean? Along the radius, towards us or away from us. And how do you measure radial velocity? Who knows the method? The shifting of frequency, called the? It could be spectroscopy, but the words that I'm looking for are the Doppler shift, the Doppler shift. The way you measure radial velocity, towards you, blue shift, away from you, red shift. That's how you measure it. Okay, Annie Cannon and the Harvard computers. What did they do? Oh, spectral classification, that's what they did. So what are the letters? You're supposed to know them in order. O, B, A, fine, giraffe, right? Goat, kiss me. Whatever, you just got to know them, okay? And what are they the order of? Why are they the correct order? What's happening? What's changing? The temperature, right? Make sure you know that. Are there any questions on classification of stars on your exam? And do you have to answer questions like which star is hotter, an F star or a K star? Yes. Okay, so what's the right answer? Which one's hotter, an F star or a K star? F, O-B-A, fine. Girl, kiss me, right? So the one that comes later is a cooler star. What's the hottest star? O's are the hottest. B, A, F, G, K, and M. M is the coolest one, right? O's are like in the 40,000 range, maybe even hotter. And M's are like in the 3,000 range. What kind of a star is our sun? You need to know that. A G class. Does anybody remember that a little bit more? G2. The letter V, Roman numeral 5, G2V. Right, good, good, good. Actually, you listen to any astronomer, they're really, yeah. Although I got scolded today. Somebody said, no, the sun is not a yellow dwarf. But Phil said so, but all right, whatever. Somebody said, no, it's not a yellow dwarf. They told me that, corrected me. I'm like, okay, all right. I don't know, I guess so. All right, could be. Don't quote me on the yellow dwarf thing, okay? So, but that's what Phil said, so I kind of like it. So. And he's kind of an expert on little stars. So anyways, all right, Hertzsprung-Russell diagram. Oh, so Annie Cannon and the Harvard computers were the ones that figured out the correct order, okay? What's a Hertzsprung-Russell diagram? So actually, why don't we just draw one, right? What do you need to know about the Hertzsprung-Russell? You need to know how to draw one or what it looks like, right? So what are the pieces of it? First of all, what are the axes? What are the two axes made of? Right, Hertzsprung and Russell put together a diagram, and on the horizontal, what do you have? The classification, and on the vertical, what do you have? The luminosity, okay? The two things we have are the classification temperature, okay? So we got our temperature right here, which is classification. We got O, B, A, F, G, K, M, right? And then we have on the vertical, we have the luminosity. And usually measured in terms of the sun, right? Luminosity. We're not going to put any numbers on here, just an idea. Conceptual, okay? So you have 90% of the stars are on this line right here, okay? And again, I'm not drawing it perfect. It's something like that. It's got a swiggle to it, okay? That's a technical term, right? Swiggle. No, okay. What's it called? The name for this line? The main sequence. What percentage of the stars are going to be on the main sequence? Like 90%. Really, like 90%. Most of the stars. Why are 90% of the stars on the main sequence? Because that's where stars spend 90% of their life. You do 90% of, and why are you a main sequence star? You're fusing hydrogen into helium in the core, okay? But you got a little group down here that you should be aware of, a little group down here. And are they hot or cool? Hot and high or low luminosity? Not very high, right? So they're lower on the luminosity. These are called the white dwarfs, right? Need to know that. If I say red dwarf, where is a red dwarf? What's red dwarf? I'm talking about a star that's on the main sequence, and it's a low mass star, and it's red in color. This is what I mean by red dwarf. Okay, some people didn't like that in the past, but I want to make sure you understand. Red dwarf means on the main sequence, a low mass, cool star. We call it a red dwarf. But a star that's on a line like this, they all have the same what? Same classification, which means the same temperature, right? They can all be the same temperature. But the higher I go, what happens to the luminosity? The higher you go, the greater the luminosity. The temperature is the same. How do you get more luminous? You are a bigger star. And so these are called the red giants. So we kept the letter red, right? Or the color red. And then up here we got the red supergiants. Okay. They're even, somebody was mad at me the other day because you didn't talk about hypergiants. Okay. If you go read about it, there's actually another category called hypergiants. But anyways, we don't need that. All right. It's just kind of interesting. Hey, you at home, did you hear me? You don't have to know about hypergiants. I just clipped that. Okay. Hypergiants, don't worry about hypergiants. Okay? But they are there. Kind of cool. All right. What's next? All right. Hertzsprung, main sequence, giants, supergiants, white dwarfs, red dwarf. Okay. I put all that on there. Great. Oh, then let's go back to the main sequence. If you look at the main sequence, what's the relationship between life expectancy and your main sequence position? So I'm going to go right here. to our G2b, that's our sun. What is the mass of our sun? Okay, it is 1. 1 because we use the mass of the sun as our scale. So it's 1 solar mass, right? And so as you go up the main sequence, what happens to mass? Bigger or smaller? Bigger, bigger. So up here we can have 2, 2 is like here, right? You don't have to know 2, but I asked you to know 100, right? 100 would be way up here, 100 solar masses. I asked you to know 1 solar mass. And the last one, way down at the end, is the end of the line. You can't go any lower than that. At the very end, 0.08 solar masses. I asked you to learn those 3. You have to memorize the numbers that go with them. How many years does the sun spend on the main sequence? 10 billion years, right? 10 billion years. How about the 100 solar mass star? How many years on the main sequence? 100,000 years, right? 1,000. That's crazy. And then down here, 0.08 solar mass is the smallest star that will light up. 5.5 trillion years. Okay, memorize those numbers. Okay, for you at home, did you get that? Okay, moving it back to the screen so you can see. Everybody good? You got the numbers? Got the numbers. Okay. All right. Okay, well, I got how many more chapters to do? Okay, what's a turnoff point? What do we mean by a turnoff point? Anybody remember that? Turnoff point? If you look at an HR diagram, it may not be complete, right? So you have open clusters, globular clusters, young clusters, old clusters, right? What do they look like? Do they look the same? Actually, I wonder if I could just put this in. Wouldn't that be great? Hey, Google, show me HR diagram for a young cluster. Ooh. Oh, that's awesome. Okay, all right. So anyways. Ooh, that's good. Okay, that's a young cluster right there. Ooh, I like this. I actually know this software. This is good software. Anyways, this is actually, I used to use this on my dissertation. All right, cool. This is a young cluster. What do you notice about it? Does it have the whole complete main sequence? You're missing which stars? You're missing the stars with the lowest mass. Why are they missing? They haven't arrived yet. They're on their way. They're going to show up pretty soon, but they're not here yet. So all the larger mass stars are there. But the younger, the stars that take longer to get to the main sequence are not there yet. It's a young cluster, right? What about compare and contrast? What about an old cluster? I bet I could just look right here. This is Astronomy 162. That sounds like a good course. Okay, there's an old cluster. What's the difference between young and old? Which stars are missing now? The upper end is missing. Does everybody see it? It's left the main sequence. So you go right here to the turnoff point, right? And you say, which star, what would the mass of a star be if it was right here? And you could use your formula to calculate the age of the cluster from that. What you need to know is finding the identity of a star that is just missing allows you to calculate the age of the cluster. So the turnoff point can calculate the age of the cluster. All right, we good? That's what you get from that. So young or old, that's what they look like. And globular cluster, what's a globular cluster? Bunch of stars. Is gravity good enough to hold them together or no? Yeah, they're going to stay together forever. Thousands of stars, they form a spherical kind of shape, really beautiful. Globular clusters, there's one called M3 we looked at the other night. It was really cool. And last term, metallicity. What's metallicity? The amount of other elements in a star, right? So what elements have to be in a star when it starts its life? Hydrogen and helium. You got to have that because that's what all stars begin with. But depending on the generation, the further down you go, the further back, the higher the generation number, the more enriched they become, right? Every exploding star seeds its matter into the cloud. And so you'll find more and more heavy elements in a star. So the first generation can only be hydrogen and helium. But in later generations, you see the metallicity, the amount of higher stuff, anything above hydrogen and helium, okay? That's what we were saying. We say metallicity because most of the elements on the periodic table are metals. But other than that, that's it, okay? And so metallicity goes up the later your generation. Is our sun a first generation star? You know that the answer must be no, because the Milky Way is 13.3 billion years old, and it's 5 billion years old. It was not born when the Milky Way started, right? So it took a couple other generations before our sun came around. Here's a formula. Brightness, the brightness formula has the letter L. L stands for luminosity over 4 pi. You don't care about that. D squared, you care about that. What's D? The distance. How far away is the star? So when you look at a star, great, you got the luminosity, and you got the brightness for the star. What happens to the brightness if you go twice as far away? If you take that star and move it twice as far away, or you move twice as far away, it becomes 1/4 as big, right? It's less bright as the brightness goes down. It becomes 1/4 as big. What happens if the distance gets 10 times as big? What happens to the brightness? It is 1/100th as much. Okay, so if some of you can make the next question connection, that would be great. What happens to the magnitude number when you take the same star and you go 10 times as far away? We just said it's 100 times dimmer. So how many magnitude numbers do you need to change, right? Up or down? It's dimmer, so you go up, 5 numbers higher, okay? So if you know the first number that you started with, when you go 10 times as far away, the magnitude number goes up by 5, right? Okay, so whatever you started with. How is parallax measured from Earth? Everybody remember how parallax is made? Measurements are made? Should I go over that again? Raise your hand, I want me to go over that. Yeah, parallax, okay. So parallax is the concept that as you change your position, right, like your eye, if you change and you blink, left eye, right eye, whatever I'm doing, whatever, right eye, left eye, right eye, then the position of my thumb appears to change compared to the wall back there. So the wall would be very distant stars, and the thumb would be a near star. It's got to be pretty close. But the further away the star goes, what happens to the shift? The further away, the smaller the shift becomes. The closer, the bigger the shift will be. That's the parallax shift, okay? So how does it work? How do we do parallax measurements from the Earth? And the answer is we stay on the Earth and we take pictures of the sky, right? So what we don't really have the capability of leaving the Earth very far, not yet, but in a few years maybe, okay? So the concept is that the Earth goes around the sun, and you got to time it just right. So here's the sun, here's the Earth going around the sun. And what you do is you take a picture of a star. Here's the star, right? Here's the star. And remember that there's background stars right here. Hey, can you guys see this or no? You got the idea? You already got it. Okay. Okay, so you start here, you take a picture of the star, and you see that it appears to be lined up with the star right here, right? That's where it was. And then you have to wait a while to get the biggest distance between shots that you can. This is called the baseline, right? So the baseline is the distance between your observations. The baseline. The bigger the baseline, the better the quality of your data will be. So you want it to be as big as you can get it. Okay, bigger is better in this case. Bigger is better. Okay, so bigger baseline. And the best we can do on the Earth is we wait how much time? So we want to be on the far side of our orbit. We want to wait 6 months, right? 6 months later. And when we do, we take that picture, we see it has moved to a new position, okay? So the definition of the parallax angle is the angle that the star appears to move in the sky. That's the parallax angle. And the distance to the star affects it, right? We said that the larger the distance, the smaller the parallax angle will be. So this is measured in arc seconds. It's actually less than 1 arc second. I should probably review that too, right? Everybody know what an arc second is? Okay, so you know what a degree is? A degree is one piece of a full circle. 1 degree is actually too big. It's way too big. So we break it up like an hour into smaller pieces. And so like an hour, how many minutes are there in an hour? 60. So there's 60 minutes inside of 1 degree. You put 1 dash right there, that's called 60 minutes of arc. It's equivalent to 1 degree. 60 arc minutes, sorry, 60 arc minutes. Okay, but an arc minute is way too big. So we have a smaller piece. What's 1 arc minute? The same thing in time. How do you shift from minutes into seconds? You're going to put 60 seconds, 60 arc seconds. So 60 arc seconds in every minute. Okay? So if you look at a degree is 60 times 60, 3,600 arc seconds. An arc second is how big parallax angles are. Even smaller than that, actually. Okay? So it's a typical parallax angle. So 1 degree is 3,600 arc seconds. And so an arc second is a really tiny thing, but that's about how big parallax angles are for stars. Okay? Like, how does standard candle work in astronomy? So what's the concept of standard candle? Standard candle means you know the absolute magnitude. So what do you do with that? You compare it to the apparent magnitude, and if it goes up or down, it tells you how far away the object must be. Okay, how parallax measurements are made. Oh, we did that already. Determine from a comparison of apparent or absolute magnitudes whether a star is closer or further than 10 parsecs. So just as a quick example, why not let's do a quick example, right? I'll give you a quick example. If I tell you the apparent magnitude is 7 and the absolute magnitude is 2, what does it tell you? Where is that star? When we look at it from Earth, where is it? Is it more or less than 10 parsecs? It's more, because when we moved it to big M means 10 parsecs. When we moved it, we got a lower number. It's a brighter star when you move it to 10 parsecs, which means it must have started further away, and we brought it closer to get it to a place of 10 parsecs. So it looks a lot brighter. Actually, it's 5 magnitude numbers, right? I happen to pick that. How much brighter is this 2 than this 7? 100 times brighter, okay? 100 times brighter. Binary stars. Okay, binary stars. You guys pretty good? We've talked about it a couple times. Binary stars. They orbit a common center of mass, and we talked about it in the first problem in the very beginning. I gave you this one already, so you know you had to know this, right? So blue shift, red shift. You got it? Okay. Differentiate between proper motion and radial velocity. I feel like I already mentioned that too. Proper motion means, what does it mean? It means towards us, away from us, or across the field of view. Which one? Across the field of view, right? Proper motion. Radial velocity means towards us or away from us. Which one can we measure easily? Radial velocity is the easy one to measure using the Doppler effect. How does a light curve work? Again, we showed you a picture. How does it work? One star is hot and one star is cool. If they're the same temperature, you won't see this effect. It won't work. But if one is hot and one is cool, when the hot one goes behind the cool one, you get a big dip, and when the opposite, you get a small dip, okay? Major categories of HR diagram, lifetime on the main sequence, and position, we talked about that. If you're higher on the main sequence, are you gonna live longer or shorter? Shorter, less time, right? Lower on the main sequence, you're gonna live longer. How does your mass change as you move along the main sequence? Bigger mass is where? Higher on the main sequence, okay? Turn-off point, we did that. Okay, turn-off point. Range of human seeing. Oh my gosh, there's so many words. Wow. Okay, 6, a change of 1, 2, 5. I've done these things with you, okay? Just make sure you see that. 1 degree. Oh, I just said the stuff, right? Said it. A parsec. I didn't remind you, but if you remember, a parsec is 3.26 light years. Oh, be a fine girl, kiss me. And spectral classification, G2V. lifetime, 10 billion, 0.08, 5.5 trillion, 100 whole solar mass, 100,000. Okay? I feel like we covered that pretty well. Okay, here we go. Oh my gosh, how can we finish everything? There's no way. All right, we're going to try. Chapter 12. Okay, remember that you don't need to know everything in this chapter. There's a lot of stuff that I don't include, so look at the study guide, right? This is the study guide. It's a very small study guide, okay? So most of chapter 12, we've either talked about it enough or it's just not as important to me. So what's important? Let's take a look. Interstellar medium means what? Stuff between the stars. How many different types of stuff between the stars can form new stars? How many different types of ISMs can form new stars? Do you remember? You don't remember. Okay, the answer is 3. There are 3 different kinds of ISMs that have high density and therefore can form new stars, right? So they are called, what are they called? First one, molecular clouds. Second one, H1. Third one, H2. Those are the top 3. So I'm missing WISM and I'm missing coronal gas. Okay, I'm missing those because I don't want to worry too much about them. They come back. Coronal gas comes back anyways. We'll get it again. So don't worry, you're going to get it. You'll get lots of coronal gas. Okay, that's not funny. All right, here we go. Okay, intercept. Molecular clouds, what do you need to know? Are they hot or cool? Very cool. The coolest kinds of interstellar medium. They're made up of what? What are they made of? Molecules. They're more complicated. There's chemistry going on. So they're really cool. And what about their density? High or low density? Very high density. Now, here's the biggest problem many students don't remember. How do we see them? How do you see them? Can you see them by the light that they glow with? No, they're too cool. So they don't glow very much. But if light goes through them, what happens to the light? Some of the colors are absorbed, and those colors will also be emitted. But the absorption lines are the key. Okay, so molecular absorption lines. H1, jumping to H1, hot or cool? A little bit warmer, still pretty cool, right? Not too hot. Actually, I think the numbers were like, what were the numbers? 100? Like 100 Kelvin. That's cool. That's actually really cool. And high or low density? H1. High density. Okay, what's special? How do you see them? Do they glow with their own light? Again, too cool. They don't glow very much. So how do you see them? And we see them by radio astronomy. We see in particular a line of absorption called the 21 centimeter line. You're supposed to know that. The 21 centimeter line detects neutral hydrogen gas. Okay, so H1, neutral hydrogen gas. It's neutral because it's not high temperature. H2 is not neutral, right? H2 is ionized hydrogen gas. It glows what color? Red. It's a reddish glow. And it's glowing because the electrons are free. When they fall back in, sometimes they emit light. Okay? One of the colors we can see is red. Photoionization is one way that gases can become ionized. Light comes in, high energy light, and rips the electrons off of the atoms. For example, ultraviolet light from a young hot star. That's a big, important example. If you have a young hot star behind a dust cloud, its energy can ionize the gases, okay? Photo meaning light, ionization meaning removing the electrons by that light energy. Reflection nebula is that the light from a star reflects off of the gases. And so, okay, so H2 are glowing with a red color. They're emission nebulas. And reflection nebulas are glowing with the light of the stars that are reflecting the light off of them. So they're usually not red. They're blue or white or yellow, whatever color the star is glowing with. Free fall time refers to the amount of time a star collapses in the formation of a protostar. So what you're supposed to know is the more massive equals less time, right? So more massive, you're faster becoming a main sequence star. Yeah.
So are H1 clouds and molecular clouds not they don't glow?
They're too cold.
Okay.
Yeah, they're too cold. So the way that they're just too cold to glow much. Yeah.
So is H2 the hottest and
of those 3, yes. And that's like 10,000 Kelvin. So it's like the surface of the sun hot.
the least dense?
and the least dense, but it's still pretty high densities. So it has, all three of those can have high densities, which means all three of them can be star-forming regions. Okay. So that's important for the next section that we're learning about, actually after this test. It's like we want to talk about galaxies, and where in the galaxies are you forming new stars? That's what you want to know, okay? That's why it's kind of important. Herbig-Haro is, so free fall time, we got that? A small mass star takes a long time to form a star, but a large mass star falls quickly and becomes a star very quickly. Herbig-Haro is a special kind of protostar with jets. What do the jets come from? Magnetic field. They have a disk, charged disk. You make a magnetic field somehow. Don't worry about it and anything else. CNO comes up again. We already know about it. Brown dwarf, what's that mean? A star that's not a star. Sorry, it's not a star. It's a large body with a smaller mass. It's too small to light itself up with fusion. Okay, so it might do a little fusion, but not be able to sustain itself. So it's called a brown dwarf. Open star cluster, stars are born together, and then they drift apart very often, including our sun probably, right? And we call that kind of cluster of young stars born together an open cluster. So gravity is not strong enough to keep them together. They drift apart. So we have other examples too. Describe differences in the various types of ISM clouds. I just went through all of that. So remember how you see them. 21 centimeters for cold hydrogen. Hot hydrogen is hydrogen alpha, right? The H2 regions, you see the hydrogen alpha. The light of an emission nebula is red. The light of a reflection nebula could be blue if the stars are blue. So some of the examples that we've seen. The reflection nebula reflects the light of the star, so it'll actually be whatever color the star is. What's the relationship to free fall? I just said this, right? Free fall time. Longer free fall means you are a smaller mass star, right? Shorter free fall time means you are a larger mass star. It means you get to the main sequence faster. And we did this already. Okay, jets, magnetic field, that's all. Okay, HR diagram of young cluster, we did that a little while ago. Okay, and we did that already. Okay, 13. Stars dying. Okay, man. I think we've done some of this, but not all of it. Okay. Type 2 supernova. What's a type 2 supernova? We have talked about that. Type 2 supernova is a larger mass star which blows up. It went all the way to iron, right? Tried to fuse iron. And the moment you try to fuse iron, you lose energy in the core, you absorb energy, it cools off, it collapses. Okay? Hydrogen shell burning, what does that refer to? What stage in the sun's life is hydrogen shell burning taking place? When it is a red giant, okay? So after the first stage, the main sequence stage, you run out of hydrogen in the core. Should we talk about this? Should we go through the steps again? So you're a star, you're burning hydrogen. You're a main sequence star, burning hydrogen in the core. You're enriching the core. The hydrogen is changing into helium ash. Is the ash burning? No, it's just sitting there. It's just taking up space, right? Not doing anything. It needs to be so much hotter to fuse helium that it doesn't actually burn. It just sits there. But little by little, you deplete your hydrogen until what happens one day? You run out of hydrogen in the core. You are no longer going to be a main sequence star, right? You ran out of hydrogen in the core. What happens to the core when you stop fusing hydrogen there? It begins to collapse because you're not making the radiation pressure. You still have a lot, so you don't just collapse all at once, but you start to compress. As you compress, what happens to the temperature of the core? It gets hotter. Okay, so you start fusing helium right away, right? No. Remember, you got to go from 10 to 100 million. It's a huge jump. But what does happen is the outside of the core area, there's an area that reaches a temperature which is hot enough for fusion to begin. And so the hydrogen around the core begins to fuse, and we call it by hydrogen shell burning. Okay? So hydrogen shell burning actually fuses more hydrogen than you did when you were a core burning. So you have more energy coming out, and so you begin your first red giant phase. Okay? It's the beginning of the red giant phase. Yeah?
Why is it shorter if there's more hydrogen?
One more time?
Why is it a shorter phase if there's more hydrogen deeper? Or is it quicker?
Like, I mean, a larger star?
Yeah, why is the red giant phase shorter?
Oh, well, because Okay, that's a great question. Why is the red giant phase shorter? The answer has to do with, the rate at which, let's see, let me see. What happens when you make hydrogen? I mean, when you make helium, how many hydrogens does it take? It takes 4. So that one hydrogen takes 4 of them to make 1 helium. It's going to take 2 heliums to make 1 fusion take place. The amount of reactions that you can have is getting reduced because you don't have as many particles available. You just cut down the number of particles by a factor of 4 in that first phase. So the amount of fuel is decreasing for each stage of the fusion game. Does that make sense? But it also will have something to do with the rate. But it's, if I had to give you a first answer, that would be my first answer. The amount of fuel that you're getting is less because it's less stuff, right? There's less particle. And so you can go through it at a faster rate. Yeah. Okay, that would be my first answer. All right, so red giant, when the sun grows, how big will it grow? It will eat up Mercury, Venus, probably Earth, okay, by Earth. And every time it does, by the way, it's going to blow out shells of material, forming what will eventually become a planetary nebula. Remember that? And the planetary nebula may not be spherical because of that. As it eats a planet, right? It'll kind of burp and, whatever. It'll make a funny little shape. It'll be kind of cool. What's the helium flash? So we said that there's hydrogen shell burning. What happens to the core during the hydrogen shell burning? It continues to collapse. There's nothing, it just is not enough radiation pressure to hold it up. So as it continues to collapse, it gets hotter and hotter and hotter, and one day it reaches 100 million Kelvin. And so the helium begins to burn. So we get the helium flash. Now you've got helium fusing and hydrogen fusing. You've got even more energy. So in principle, you could even get larger, right? You can get even larger as a result. Okay, meanwhile, the whole time, the sun is going to be shedding material, and it will end up losing almost 80% of its mass during the red giant phase. This is huge. It's kind of important that you get that. So that by the end of the whole red giant phase, the only thing really left is the core, whatever the core is. Everything else gets blown away. And then what happens? The sun runs out of fuel. What does it do? It collapses and forms the sun will form after the red giant phase, a white dwarf. And that white dwarf is really hot, so it will shine with very hot light, meaning ultraviolet light, and it'll light up all those gases that have been ejected, and you'll get the planetary nebula again, right? The planetary nebula. Okay, Messier objects are a whole bunch of different things studied by Charles Messier. You don't really have to know much, just there's 110, you don't even need to know that. What are they? You don't even need to know that. There's a whole bunch of things that are cool. And this guy named Messier figured them out, found them first. He was looking for comets. You don't even need to know that. What do you need to know? I don't know. I don't even know why it's on the study guide, come to think of it. But they're kind of cool. They're kind of cool. Messier objects. If you want to study astronomy, they're some of the best things to look at. They're clusters, they're nebulas, they're galaxies, binary star systems. They're kind of neat. Okay, other than that, don't worry, okay? Roche lobe is referring to what kind of process? Roche lobe. White dwarf with a red giant companion, okay? So when the red giant is spewing off shells of material, the white dwarf will say, hey, let me have some of that. And what has happened is the material has crossed over into the gravitational region near the white dwarf. So that's called the Roche lobe. And at that point, it's going to come on to the white dwarf. It's going to be a what? A nova, right? Okay, Chandrasekhar limit, very important for what kind of stars? What kind of objects, rather? For white dwarfs, right? It is the limit for how big a white dwarf can be. You can't go above this limit. What is the limit? 1.4 solar masses. If you are a white dwarf, you must be below the limit. But if you keep grabbing matter from a red giant, right, it could be that you end up exceeding the limit. And if you do, what happens on that day? You become a type 1a supernova, right? On that day that the white dwarf went above the limit, the electron degeneracy pressure can't keep gravity from from collapsing it anymore. And so it collapses and instantly fuses, or not instantly, but pretty quickly fuses all of that stuff, carbon and oxygen, and you get a type 1a supernova. Do we know the mass of a type 1a supernova? Yes, 1.4 solar masses. That's the Chandrasekhar limit. So do we know the magnitude, the absolute magnitude of a type 1a supernova? Yes, we do. And we know what the light curve looks like. We know it really well. And as a result, they are one of the best standard candles for measuring distance in outside of our galaxy, distant galaxies. Okay. Electron degeneracy pressure is found in what kind of object? Electron degeneracy pressure. White dwarfs, right? White dwarfs don't collapse. Gravity pulls in, electrons push back. Are they stronger or weaker or the same strength as gravity? They balance gravity, right? They're strong enough to stop gravity from collapsing. Neutron degeneracy pressure is found in what kind of object? A neutron star, right? Neutrons push off of each other and push against gravity and are strong enough to stop gravity. Okay, a nova occurs when a white dwarf feeds on a red giant, right? Little mass dropped in. Type 1a, weak nuclear force, already did that, right? Got it. Stellar ejecta, material that is thrown away from the star, pushed away from the star during the red giant or red supergiant phase, especially, right? In these phases, the star is so large that the edge of the star is not bound very well to the star, and so it escapes. You get shells of material escaping. Thermonuclear runaway would be referring to the type 1a supernova, right? The nuclear reaction occurs very quickly. Supernova light curve is something that you won't have to worry about. I put it on there, but don't worry about it. And actually, our friends out at LCO watch supernovas on a daily basis. And it turns out, I told you, I don't know if I did. You should know this. Do we know the mass of a type 2 supernova? Do we know exactly what the mass is? No, we just know you started with a star more than 8 solar masses, but I don't know what it is. It could be 100 solar masses. I don't know, right? So that's a problem. Can we use type 2 supernova as a standard candle then? You would think no, right? And I would tell you initially no. But our friends at Las Cumbres Observatory are learning how to watch the star get brighter and dimmer, and from that information, extract the mass of the star, okay? So I would say, yes, that's true, you can't. But I would also say that if you're an expert in the field, it's something that you're learning how to maybe do, okay? So it's not a good standard candle yet, but we're working on it, okay? Pulsar is a rapidly rotating neutron star. We have jets shooting out of it. It looks like a lighthouse, and that's coming from the magnetic field, right? Magnetic field. Neutron star is amazing. Gravitational waves are amazing. I should keep talking, right? What's a neutron star? How do you form a neutron star? What has to happen? Neutron stars form after a type 2 supernova. What's left over? Well, nothing except the iron core, right? That's nothing left except the iron core. If the core mass is between blank and blank, you will form a neutron star. What's the numbers you're supposed to know? 1.4, more than 1.4, and less than, I said 3. Okay, I might be wrong about the 3, but it's close to that, right? And that's the number you want to remember. So it's some of the densest material we can talk about. Gravitational wave is ripples in space-time, right? And we've learned recently, just really recently, a few years ago, we've managed to feel it. Did you sign in, Mason? Mason, did you sign? The tennis sheet, you get your extra credit. Okay, and grab some candy on your way out, man, if you want. All right. Okay, so neutron stars, when they merge, they have 2 neutron stars merging together. You get a kilonova. You're supposed to know about kilonova. Quick, what's the quick thing? It's the merger of 2 neutron stars creates lots of really cool elements, right? Gold, silver, platinum, all that stuff. You don't have to know all the elements, just that it creates a bunch of stuff in that procedure. What you need to know is that it forms gravitational waves, and the most important thing, we can see it as well, right? How is this different from the merger of 2 black holes? The black holes merge, you don't see anything. There's nothing to see because the black holes don't let light escape. Now, if the black holes had accretion disk, you could see that. But anyway, so in two neutron star merger, you can see the light and you can feel the gravitational wave. Okay, I don't think I ever told you this. Did I ever tell you this? Oh yeah, I did. I told you this story. In Messier 1, Charles Messier 1, they saw this cloud of material and they measured the size of it. And then a few years later, like 20 years later, they measured the size again and they found it had grown. That was pretty cool. It was the first time anyone had ever seen that. And of course, the first thing they said is, well, if it's growing, then it must have been smaller a little while ago, right? And they managed to calculate the birth date of this cloud. And they found it was about 800 years before the observation. Well, that was about the year 1054. So they went looking in the literature, in the writings of astronomers, astrologers, and they found that in China, the Chinese astrologers had recorded the presence of the guest star of the year 1054. And it was remarkable because it was so bright, it could be seen during the day for about 21 days. For 21 days, you could actually see it during the daytime. And for 2 years, you could still see it at night. And then it faded away. So it was a guest star. And we found out that was really the first supernova that we'd ever seen before. Okay, supernova. How does matter get lost in a giant or supergiant stage? It's very far away from the center. And so the giant is going to blow it away in shells, right? So shells of material will leave. And this will end up giving rise to this thing that we call a planetary nebula. Okay, so it's the shells of material that get blown away. Why do they sometimes lead to funny patterns? Right? I said one reason might be that they're eating their planets. Right? We now know how many planets there are. Every star has planets. So now I even like the idea better. A few years ago, I didn't even know how good this idea was going to be, but I like it a lot. And it's not the only idea. There's other ideas. Magnetic field might be another capability, but it's really easy to understand why swallowing a planet would do something to you, right? You're going to expect that you're going to get a cloud of material that might be a little bit asymmetric, okay? How does the final mass of the core? Okay, so we did this. I think we did this quite extensively. If your mass is less than 1.4, you can only be a white dwarf. If you're between 1.4 and 3, you're a neutron star. If you're greater than 3, nothing can stop gravity, and you become a black hole. Okay, I have not talked to you about this. This is a mystery. You can actually ignore that. It's not on your test. But it is a mystery. It's actually a kind of mystery. So we can't see as many pulsars as we expect. Okay, and there's actually a pretty simple explanation, but we've even tried that, and it's probably not right. And that would be that the pulsars are not pointing towards us, right? Maybe not. I mean, why do they have to point to us, right? There's no reason they have to. But it turns out that statistically they should be, and we don't see enough to see that. That's kind of interesting. What happened on August 17, 2017? Kilonova. That is really important to me. I think it's just amazing. And in my mind, it's changing the whole field of astronomy. That's why it's so important. Everything is going to change. And I'm already feeling it. Like literally 2 weeks ago, they started LIGO back up again, and we're already hearing about gravitational waves. It's going to be great. Okay, small, medium, large stars. If you're less than 8 solar masses, what are you going to end up with? You're going to be a white dwarf. Okay. Between 8 and 20, you probably form a neutron star, and greater than 20, you're going to form a black hole. Okay, you just have too much mass, and you're going to have too much mass left over at the end. Okay, our final chapter, chapter 14. It's real fast. Okay, you don't need a lot of stuff. It's basically a few key ideas. I'm going to go all the way because that's what I want to do. Okay, I don't have to teach until 7, even though I have to print up your exams. I'm going to go, okay? If you want to leave, that's okay. Take some candy as you leave. Make sure you sign the roster. Those of you at home, sorry, there's no candy for you. But come to my office if you want. All right, so we're going to talk about black hole. What makes a black hole? See you later. Okay, see you tomorrow. All right, so black hole is the ultimate. It's absolutely horrible, terrible thing, okay? Wonderfully terrible thing. The gravitational force is so profound that nothing stops gravity. And so it shrinks smaller and smaller. And I don't want to talk about it, but we're going to talk about it anyways, right? You form a point mass, right? You form a point where all the matter is located. What's the name of that point? I don't know if the word's up here. Oh, there it is. Singularity. Oh, I hate that word. Okay, singularity. So the point where all of the mass is located. Now, there is a little bit of something important that maybe would make you feel a little bit better, make me feel a little bit better. It turns out that in the process of bending space-time, the energy required to bend space-time is being extracted from the matter. So actually, after the black hole forms, there may not be actually any matter left anyways. But you still have a singularity, so I still have a problem. Okay, so anyways, that makes me feel a little, not really. I'm still unhappy about it, okay? And you have infinite density, even if you have almost no mass, anything at all. Okay, special theory of relativity is one of Einstein's theory. What does it relate to? It is when things are going very fast, okay? There were two postulates that he came up with, and it's listed down here. The two postulates of special relativity state that for observers moving in inertial reference frames, number one, the laws of physics will be the same. And number two, the speed of light will always be the same. That's it. Okay, that's it. Simple. It's not, it's complicated, but those are the two simple ideas. From those two ideas, all of the rest of the stuff comes out. So actually, let's jump right to the ideas that you need to know. So in special relativity, there are three big ideas, and they're all based on the same formula, which you don't need to know in this class, but I just want to write it down anyways, just so it's easy to write the other formulas down. So there's a factor by which special relativity is acting, and that is called gamma, the Lorentz factor. You don't actually need to know any of this part, except that it's a number, and the number gets bigger the faster you go. See you later. Okay, so it is 1 divided by the square root of 1 minus v squared over c squared. You don't need to know this, okay? It's just a factor. It's called gamma. And gamma is the factor by which all of this stuff is going to manifest, right? How are things going to change? The key thing is that larger v gives you a bigger gamma. That's the key thing. That's all you need to know, okay? The larger the velocity, the bigger gamma becomes. Now, I actually could have done something really simple. What happens if the velocity is 0, just so you understand? If the velocity is 0, this is gone. What's the square root of 1? Can you do that in your head? Just kidding, right? So if you get v is 0, then gamma is 1. There's no change, right? It doesn't do anything. And that's actually one of Einstein's ideas that was really cool. He says, if I'm not going fast, then I should get the standard laws of physics, the things that I'm used to. And he does. He gets them perfectly. Okay, so what are the three effects that you need to be aware of? So we're going to first need to describe what we mean by these reference frames, right? So I've got a rocket. And here's my rocket. And the rocket is moving with a velocity. Well, you have to say relative to what, right? If I measure a velocity, am I on the rocket? If the rocket has a velocity, I'm not on the rocket, right? If you're on the rocket and you measure the velocity, what would your velocity be? 0. You're in that frame of reference, right? But if I'm on the Earth watching them go by, so one of the people is on the rocket and another person is on the Earth. These are two inertial reference frames, right? So one of the people is going to be in the rocket, the other is on the ground. And again, I shouldn't do this, but I'm going to just mention it. One of the quandaries that you have with special relativity is if you're in the rocket, you're not moving. And what is the Earth doing? It's moving away from you at the speed that you think that the Earth says you're moving away from it, right? So who's moving? Depends on where you're standing, right? In fact, both people can say the other one's moving, right? That's a quandary. It's not a quandary. It's okay. We got this. But in our class, we don't worry about it. So don't worry about it. Never mind. I shouldn't have said anything. Okay. Anyways, relativity works both ways. But the key thing is that there are three major effects. Okay. So when you measure the time on the rocket ship, it is called the proper time, right? Proper time. We mentioned that if you did the experiment on the rocket, that's why, in fact, it's called the proper time. The time measured by a person who's watching is not the same. And that's a really crazy thing, but it's known as time dilation. Okay, so effect number one. If you watch a rocket go past and you ask, how much time do I see them experience? And at the same time you ask, how much time do I experience? It will not be the same amount of time. It will be gamma times the proper time. So whatever this factor gamma is tells you how much of a change you get. And the factor gamma is going to be bigger than 1. The faster you go, the bigger gamma becomes. If you're going 0.995, the speed of light, 99.5%, the factor is 10. That's how big gamma would become. You've got to go pretty fast for this to be important. But the idea is you will experience 10 times as much time as the person on the rocket. When the person on the rocket comes back, they will have aged 2 years, and you will be 20 years older. Right? That's bizarre. Time dilation. Okay, time dilation. Second effect is called length contraction. So if we measure the distance to a star, right, that length is called the proper length because we measured it in the same reference frame as the star. That's where we measured it. We're on the Earth, we're around our star, and the other star is not moving relative to us. In the rocket, we would find out that the length or the distance is not as big. And so the term is length contraction. Okay? The length as measured by the people on the rocket is the proper length divided by gamma. It seems to be closer than it was when you were on the Earth. So that's kind of cool if you're trying to get to another star. If you can go fast enough, the distance will appear to shrink to you. Right? Makes it, you get there faster. Right? You get there, but actually we already knew that you get there faster because of this time dilation effect. But anyways, it also explains why you get there faster. If you're on the rocket, you could then talk about how long it takes and you would get the same answer as the other people, right? So what you experience is what you experience. Okay, the last thing that happens is if you think about the mass of an object, the mass of an object at rest is called the rest mass. I'm going to put an M0 because I don't want to put a P on it. But it's called the rest mass. You could say proper mass too, but we don't. We call it the rest mass. This is what Einstein called it. So the mass of something at rest is this mass here, the rest mass. If you make it go really fast, it acts as though it does in fact have more mass. And the mass of the object is gamma times the rest mass. So the faster you go, the bigger the mass appears to be. Because of this, you can never go the speed of light. The closer you get, the larger the mass becomes, the harder it is to make it move in any way. And therefore, you can't speed it up. You can't go the speed of light. You have to stay less than the speed of light. All right, so that's why that stuff is important. So we got special relativity, 3 key things: time dilation, length contraction, relativistic mass. Okay. Okay, time dilation, rest mass, space-time. Okay, space-time is the concept that space and time are connected to each other. I don't know how to describe that. What do you do? Just say that. Whatever. Yeah. The cloth thing, right? I gave the demo of the cloth thing. It gets deformed by gravity. That's actually not special relativity, but anyways, whatever. Okay. All right, so now we get to general theory of relativity. General theory of relativity says that in gravitational fields or during acceleration, we will see changes in our reality. We will feel things, right? So if you are in a rocket ship that's accelerating, you can feel as though you're back on Earth. And in fact, you cannot tell the difference. So he called it the equivalence principle. I don't see that word there. But the equivalence principle states that you cannot tell the difference. There's no perceptible difference between an accelerating reference frame and a gravitational field. They feel exactly the same. And so if you do an experiment, they are in fact the same. So that's a weird idea, but that's what he said. And as a result of general relativity, we're going to have two two big ideas and then one kind of smaller idea, although it's a stretch. Okay, that was a joke. Wasn't very funny. Sorry about that. Okay. Anybody get the joke? A stretch? No? Okay. Spaghettification? No? All right. Yeah, okay. All right. So general relativity is about gravity, about gravitational fields, or about acceleration. And so the one place that it matters a lot is near a black hole, right? So I'm gonna segue away from the thing just to go over the topics in a way that makes more sense to me. So I have this black hole, and it has a size, and it's not a hard size, it's a mathematical size. And this size, this boundary that I'm showing is a circle, but it's really a sphere, right? The shape is a sphere. And it's a special place mathematically. And why is it special? Well, here's why. We just said that an object that has mass cannot move as fast as the speed of light. And it certainly can't go faster than the speed of light, right? You can't even go the speed of light, let alone go faster than the speed of light. If I'm very far from a black hole, I can get away from the black hole. We call that the escape velocity. The escape velocity is the velocity needed to get away from the black hole. But the closer I get, the harder it is to get away. The larger the escape velocity will be. So black holes are incredibly compact. And as a result of that, you're very close to the mass, which means the gravitational field is profound, right? And so it turns out that at a certain distance from the black hole, the escape velocity is the speed of light. So that's a special place, right? That's mathematically, first of all, if you're matter, you can't be that close because you can never go the speed of light. But it turns out even light is affected by the gravitational field. And so if you're at this distance or closer, even if you're light, you can't get away. So that's why it is a black hole. Nothing can escape. The escape velocity from in here is greater than the speed of light. You can't get away. So this is a special place. The name for this you need to know is called the event horizon. So the definition of event horizon, the place, a mathematical distance from the center of the singularity, well, I use the word, the mathematical distance from the singularity at which the escape velocity is the speed of light. It has another name from the guy who first invented the formula for it, and the other name is the Schwarzschild radius. So if you take a more mathematical version of this class, Schwarzschild. I think I spelled it right there, right? So I spell it right? Schwarzschild, right? Schwarzschild. Oh, there's no T? I feel like there's a T. Maybe there's no T. Oops. I think there's the T. I think I messed up. Schwarzschild. I think there's Schwarzschild. Is there a T? No. There's no T? Do you know? You don't know. You'd want to know. Schwarzschild. Oh, there's no T. Okay. Okay. My study guy's right. I'm not. Okay, take away the T. No T. Sorry about that. Okay, no T. No T in Schwarzschild. Okay. So the Schwarzschild radius is another name for this distance. Okay? So it's the distance at which the escape velocity is the speed of light, the event horizon. Okay? So if you're getting close to a black hole, what are the key things you need to know? The closer you get to the black hole, the stronger the acceleration of gravity will be, the stronger the gravitational field. It turns out that a clock at position 1 or a clock at position 2 will not run at the same rate, right? So the clock will tick slower, where? Closer or further? The closer you are to the black hole, the slower your clock will tick. If you've seen the movie Interstellar, there's this one scene, spoiler alert, where they go down to the surface of a planet, and every hour that they spend down here is 7 years for their friend who doesn't come down to the planet. This is the kind of thing, and they did the math, by the way. This is a real effect that you could get if you get really close to a black hole, right? Incredible, right? So, all right, so this is called gravitational time dilation. So gravitational It's up there, right? Gravitational time dilation. Gravitational time dilation. Oh, it's not even there. What? Oh, yeah, time dilation. Okay. Well, okay, so gravitational time dilation. Gravitational time dilation. What would it say? If you are closer to the black hole, the gravitational field is stronger, or you're accelerating more, the clock ticks slower. Okay? Yeah.
So like theoretically, this could be used for time travel.
What was that?
This could be used like travel through time.
You are traveling through time right now, my friend.
But faster or slower.
Yeah, of course. Absolutely. Yes, you could go fast or you could find a black hole. Yes, that's right. But you're already time traveling, right? You're moving forward in time. Actually, I'd like you to experience the moment right now. No, you can't. See, you've already moved forward, right?
But I'm not getting ready to.
Yeah, no, you're not. You already passed it, right?
Wow.
You just passed it again. You just passed it. You just passed it. Anyways, okay. Sorry, we got to waste time. All right, so the singularity we said, what's that? That's the point at the middle. The event horizon, Schwarzschild radius, tidal forces. There's another one. Tidal forces. If you were to try to fall into a black hole, which would kill you, but let's say you just did it for science, right? For science, right? Now here you are. You're going feet first, right? So the force of gravity on your feet is stronger than your head. What will happen is you will get a tidal force. You're going to be stretched, right? You're going to be stretched. Do you remember that idea? Tidal force. So the tidal force says that if there's a difference in the force of gravity, what it ends up doing is stretching the body in the direction along a radius. I didn't draw it very well. Sorry, it's supposed to be along the radius. Okay? And so we have a name for this, right? Because it's going to be extreme near a black hole. We call it spaghettification. Okay, that's the concept. So you're going to be pulled into a strand. Actually, it's even worse than that. You're probably going to be, your atoms are going to be ripped apart from one another. Okay, so you're not going to be spaghetti. You're going to be a stream of atoms. But whatever, you're dead. Okay, how do you die? How well do you die? Okay, gravitational redshift is the last of the ideas. If I shoot a photon away from a black hole, the frequency changes. It's like whatever, just stop. It effectively loses energy. Okay, effectively it loses energy. The photon starts with a frequency f1, but if I look at it out here, it's not going to be the same frequency. The frequency of the light that I see is lower, right? It's a lower energy photon now. It's like it loses energy getting out of the gravitational well, okay? So anyways, the frequency that you see outside or further away is less than the frequency that was emitted. And this is called the gravitational redshift. Gravitational redshift, okay? Grav redshift. Okay, what's left? A couple little things. Okay, I mentioned muon. I didn't talk about it though, because I ran out of time during the lecture. But there are these particles that are being created all the time in the upper atmosphere of the Earth. And they're being created by cosmic rays coming from distant galaxies. Actually, not from our galaxy, from different distant galaxies. They hit the atmosphere of the Earth, and the energy creates new particles, E equals mc squared. We think muons are created in these events. We know that they are, actually, sorry. If you take a muon and you hold it in your hand, and you measure how long it lives, you'll find it's really short, like millionths of a second kind of thing, really, really short. So here's the question. If it's created in the upper part of the atmosphere, do you think it could make it down to the surface of the Earth? And the answer is at millionths of a second? Really? It would have to be moving near the speed of light. Oh, well, they are. They're moving near the speed of light. But it turns out if you do the calculation, using the time millionths of a second and speed almost the speed of light, you get like not even a halfway through the atmosphere. So they don't make it. But when we go and look for these muons out in the world, we find them. They do make it to the ground. And so the question is, how is that even possible? They shouldn't. And the answer is, they're not in our frame of reference. They're moving really fast. So what effect of special relativity do we have to think about? They're moving really fast. They're on a rocket ship. They are the rocket ship, right? Moving really fast. Time dilation. So they don't live millions of a second. They live 10 times that, much longer than we would have expected. And that's enough to make it to the surface of the Earth. So the fact is, when we measure these muons at the surface, we know that they're living much longer than they should. One of the cool things, again, you shouldn't know this, but I'm going to tell you, that we have muon detectors for is they're taking them into the ancient pyramids and other archaeological digs around the world. And they are using muon detectors because the muons can actually pass through big chunks of stone, but not entirely. They actually get depleted a little bit. And so what they can do is very carefully measure how much rock they had to go through. So they are using these in the Great Pyramids of Egypt to find if there are any secret rooms. Because if there's a secret room, there's no rock there, then they'll penetrate a little bit deeper than they would have otherwise. The rate will be a little bit higher. So by measuring the rates of muon counts, this is one of the cool things that they're doing. Anyway, so muon detectors are actually kind of neat. All right, so muons, okay, gravitational lensing, again, we'll learn not much more. Okay, sorry, this is it. This is it right now. Gravitational lensing is the concept that gravity bends light. So one of the most amazing things I should have shown you and I didn't because I ran out of time, but you guys are here. You will be the only ones to understand this. Gravitational lensing. It is the most amazing thing. I want you to take a look at that. That is a picture that has been taken with the Hubble Space Telescope. And it's the most amazing thing ever, right? This is either the freakiest looking galaxy or something else, right? So this is a relatively nearby galaxy. That's a galaxy called an elliptical galaxy. We'll get to that next week, okay? And behind the galaxy, there is another galaxy that we should not be able to see. It's exactly behind it. And what's happening is the light is spreading out in all directions, but some of the light is close enough to this other galaxy that it gets bent around it, and we're seeing it as a ring of light around that. Isn't that amazing? So this ring was postulated by Einstein. It's called the Einstein ring. He said if it's perfectly aligned, we might see objects that are behind other objects because the light gets bent around them by the gravitational field. Yeah?
Why does the gravitational field pull it in?
Gravity affects light. Oh, because
Yeah,
okay, so here's where the object's mass is. Here's where space-time is distorted. There's no galaxies out here. So it's bending the light where the matter is located. So we don't see the rays that are further away because they don't get bent enough. But we see the ones that are just bent perfectly around. And it acts like a magnifying glass and gives us the picture like that. That's gravitational lensing, okay? So happiness, that's a good thing. All right, singularity, muon, cosmic rays, tidal force. Okay, supermassive black hole. I didn't talk about this. Oh my God, how did I not talk about this? You don't know what a supermassive black hole is, or do you? Am I going to talk about this? Oh, I'm still going to talk about it. That's okay. So the supermassive black hole at the center of the Milky Way is known as, I'm going to talk about it. Don't worry, you'll get to hear this. Is Sagittarius A star. It's really big, okay? So really big. It is not a single star that turned into a black hole. It's a supermassive black hole. So this is a special category. We don't exactly know how they're made, but we do know that the mass of the black hole at the center of the Milky Way is about 4 million times the mass of our sun, right? It's pretty massive, super massive, right? And so that's interesting. Okay, that's about it. That's way too much. You're not going to need a lot of that stuff. Okay, twin paradox. I didn't talk about that. Oh, we're almost done. Let's finish. Okay, here we go. What is the postulates? We said those, right? Laws of physics are the same. Speed of light is the same for all inertial observers. What's the twin paradox? A twin gets on a rocket. Twin stays on Earth. The twin in the rocket takes 2 years going out and back. The twin on the Earth ages 20 years, right? And that's okay. It's weird, but it's okay. That's pretty strange. Explain the impact on mass as an object approaches the speed of light. What happens to your mass? It gets bigger, right? And if you Theoretically, when the speed of light, you would have infinite mass, not possible. What is the event horizon? Why is it the edge of the black hole? If you get any closer, what can escape? Nothing can escape, not even light. It's the edge, right, somehow, of the black hole. What would happen? Ooh, I didn't tell you this. Oh, I could tell you this right now. What happens if you watch someone drop into a black hole with a flashing laser, okay? Someone's got a nice, beautiful violet laser. It's really cool, powerful, and they're shining it every second. They're blinking it at you, okay? And then they fall into the black hole. They're going to die, but before they die, you're going to see the laser change, right? Tell me how it will change. Number one, what will happen to the time between the blinks? Will it get longer or shorter? It'll stretch out because their clock is going to go slower. You're going to see the blinks take longer and longer and longer the closer they get to the event horizon. In fact, if you like this kind of stuff and you want to do even more, there's a class called Black Holes. We talk more about this. But anyways, theoretically, if you get to the event horizon, you don't see the light anymore because the blinks take infinite time between them. Okay, so anyways, that's one thing. So the blinks get longer time between them. It doesn't blink as often. And what happens to the violet color? Does it stay violet? What does it change to? Well, it gets red shifted. What would be a color that would be okay? Violet turns into red even. Okay, it could have been green, orange, anything below violet in frequency. And how about infrared? Would that be okay too? Yeah, that's what happens eventually, right? And all right, so that's what happens. And then you would watch their body get ripped apart. They'd die. Okay. Explain how we know. Oh, I'm supposed to tell you this. Shoot, I forgot. How do we know there's a supermassive hole at the center of the Milky Way? You don't know. Never mind. Okay, just kidding. I'll skip it for a second though. How do we see most black holes? Do we see the black holes themselves? No. What do we see? The accretion disk around it. Okay, so the very last thing, again, for those of you at home, I'm so sorry. I really failed as a teacher. I did not show you something important, but you're here, so you'll get to see something cool. How do we know there's a supermassive black hole at the center of the Milky Way? Ready? This is it. For 25 years, Harvard University and another consortium of astronomers have been watching the center of the Milky Way, and it's called Sagittarius. I'm going to just tell you the A star, okay? Sagittarius A star, Sagittarius A star, videos, Stagger A star, Stagger A. Let's see. Is this okay? That's a person's bio. Never mind. Okay, let's see. Okay. All right. Okay, Milky Way. Supermassive black hole, Milky Way. Okay. Okay, here we go. So I don't have 20 minutes. Oh, I don't have 20 minutes. 20 minutes is too. No, I don't have 20 minutes. I wanted this little quick clip. 2-minute clip. Not that one. 16 seconds. Okay, we're 12 seconds. Okay, that might work. Oh, this one's good. That's 3 minutes. Okay, all right, 21 seconds. Okay, this is pretty good. Okay. Okay, so this is actually an image taken from infrared astronomy. The telescopes look very carefully behind the dust that's obscuring the center of the Milky Way, and it's able to watch stars near the center of the Milky Way. It's very dense, densely packed, but each one of those little globs is a star. And they've been watching for the past 25 years, and they've been watching them move, okay? And so you want to understand that something interesting. So Keck, UCLA, and Harvard University. Oh, come on, really? No, please, come on. Come on, there you go. It's YouTube. Okay, you'll notice that they put a little star there, but there's actually nothing there. And you see the stars looping around. They're looping around this invisible, oh man, went away. Okay, they're looping around this invisible point, and there's no way that could be anything except for a black hole. Come on, loop. Okay, so if you look carefully, you can see this one, actually it only took 21 years to make a complete lap. This object must be incredibly massive. The only thing it could be is a supermassive black hole. And so we've been able to calculate the mass of the black hole by the masses of the stars as they orbit around this invisible spot. Okay, so it's there, it's real. This is actually the best detection before the stuff that we saw last week. This is actually one of the best experiments. Yeah.
What would SC17 have to be to go kind of like straight line?
One more time, sorry.
What would SC17?
Yeah.
Kind of like really close straight line. How big would that?
Oh, SC17, the loopy one?
Yeah. No. Straight one.
Oh, the straight one. Oh, it's going right through, you think? Yeah, I don't, it might be, so here's what's happening. It's not going straight through. It's actually, it's looping behind or in front in a way that you can't see the motion. Yeah, you can't see it. You know that, right? It can't be. This thing is huge. And so its gravitational field is warping.
That's what I was wondering.
Yeah. So it just turns out we're aligned in the plane, maybe. We're aligned with the plane. We're not seeing the path. Okay, well, thank you guys very much. Have a good day. We'll see you tomorrow morning. Good luck. You're welcome. Bye. Bye, everybody. Hopefully the sound was better. All right. And that's